Hello there, and welcome to Nightfall Science. Tonight, we drift gently into one of humanity's oldest questions. Are we alone, or is life quietly waiting somewhere among the stars? Let your shoulders ease away from the day, and let your eyes grow heavy whenever they wish. The universe has carried this question for billions of years, and it will keep glowing softly while you fall asleep. Let's begin. The search for life begins with one small blue world. Earth is the only place where life is known to exist. Every ocean, forest, cloud, field, desert, and living cell belongs to one confirmed example. This makes Earth precious. It also makes Earth useful. To search for life elsewhere, science first studies the only life it can touch. Life on Earth is made from familiar ingredients. It uses carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and many other elements. These atoms are not rare in the universe. They form in stars, drift in gas clouds, settle into planets, and become part of rocks, oceans, and atmospheres. In that quiet sense, life is made from cosmic material. The deeper mystery is not whether the ingredients exist. The mystery is how they arrange themselves into something alive. A living cell is not just chemistry. It is chemistry that stores information, takes in energy, protects itself, and makes copies. It is matter that has learned to continue. Earth shows that this can happen at least once. It happened on a rocky planet, orbiting an ordinary star, in an ordinary galaxy. The Sun is not the largest star. The Milky Way is not the only galaxy. Earth is special to us, but its ingredients are not unique. That is where the question becomes soft and wide. If one small planet became alive, perhaps another quiet world has done the same. Water is the first gentle clue. When scientists search for life beyond Earth, they often begin by looking for liquid water. This does not mean water is magic. It does not mean every watery place is alive. It simply means water is one of the best places for life as we know it to begin and continue. Water is a remarkable liquid. It carries dissolved chemicals from place to place. It helps molecules meet. It holds heat gently. It can flow through cracks, gather in oceans, rise as vapor, fall as rain, and freeze into protective ice. On Earth, water links the sky, the land, the sea, and living things. Life on Earth uses water inside its cells. Tiny reactions happen in it. Nutrients move through it. Waste leaves through it. Even in places that seem dry, life often waits for a trace of moisture. A desert seed can rest for years, then open when rain arrives. A microbe can survive in a thin film of water hidden between grains of salt. This is why water becomes a guide. It gives scientists a soft direction in the darkness. Mars once had rivers and lakes. Europa may have an ocean under ice. Enceladus sprays water vapor into space. Distant exoplanets may orbit where surface water could remain liquid. Water does not answer the question alone. But wherever water rests for long enough, the universe seems to become a little more interesting. The habitable zone is a quiet ring of possibility. Around every star, there is a region where a planet might receive the right amount of warmth for liquid water on its surface. This region is called the habitable zone. It is sometimes called the Goldilocks zone, because it is not too hot and not too cold. But the real idea is more delicate than a fairy tale. A planet in the habitable zone is not automatically alive. It is not even automatically comfortable. The planet also needs the right kind of atmosphere. It needs enough pressure for water to stay liquid. It may need clouds, oceans, volcanoes, seasons, and a climate that can remain stable for a long time. Venus and Mars show why this matters. Venus is closer to the Sun than Earth, wrapped in a thick atmosphere that traps heat. Mars is farther away, with a thin atmosphere and a cold surface. Earth sits between them, with oceans that have lasted for billions of years. The habitable zone is not a promise. It is an invitation to look more closely. A planet may orbit in the right place and still be dry, frozen, or airless. Another world may orbit outside the classic zone, but hide a warm ocean beneath ice. Habitability is not one simple circle. It is a balance between light, air, rock, water, chemistry, and time. Still, the habitable zone gives the search a gentle starting point. It is a soft band of starlight where a world may hold a sea. Planets are common in the Milky Way. For most of human history, no one knew whether stars like the Sun had planets of their own. People wondered. Philosophers imagined distant worlds. Writers filled the night with other Earths. But the proof came slowly. Today, thousands of exoplanets have been confirmed. These are planets orbiting stars beyond the Sun. Some are huge gas giants, larger than Jupiter. Some are rocky worlds closer in size to Earth. Some orbit two stars. Some circle very near their suns, completing a year in only a few days. Some drift through deep cold, far from the warmth of their stars. This discovery changes the feeling of the night sky. A star is no longer just a distant point of light. It may be a sun with worlds around it. It may have planets with clouds, storms, mountains, rings, moons, and silent horizons. Many exoplanets are found by the transit method. A planet passes in front of its star, from Earth's point of view. The star dims by a tiny amount. That dimming repeats each time the planet orbits. From those small dips, scientists can learn the planet's size and orbit. It is a gentle kind of discovery. Nothing explodes, nothing announces itself loudly. A hidden planet simply crosses its star and leaves a small shadow in the light. In that tiny shadow, an entire world becomes known. The Kepler mission showed that planets are not rare. NASA's Kepler Space Telescope stared at a single rich patch of sky. It watched the brightness of many stars, looking for the tiny dips made by passing planets. Over time, Kepler transformed the search for other worlds. It revealed that planets are not unusual. They are one of the galaxy's ordinary habits. Before Kepler, the solar system could still feel like the main pattern. 4 rocky planets near the Sun, 4 giant planets farther out, small icy bodies beyond them. But Kepler showed that other systems can be arranged very differently. Some stars have planets packed tightly around them. Some have worlds larger than Earth but smaller than Neptune. These are often called super-Earths or sub-Neptunes. Our solar system has no planet like that, yet they appear to be common elsewhere. This is one of the calm surprises of astronomy. The familiar pattern is not the only pattern. Nature makes many kinds of systems. It builds planets close to red dwarf stars. It places giants in tight orbits. It creates worlds with sizes and paths that once seemed strange. Kepler did not find life. It did something quieter first. It showed that the galaxy has countless stages where life might possibly appear. A question that once belonged mostly to imagination became part of measured astronomy. The stars did not become less mysterious. They became more filled with worlds. TESS searches the nearby sky for new worlds. After Kepler, another mission continued the work in a different way. NASA's Transiting Exoplanet Survey satellite, known as TESS, looks across most of the sky. It searches bright nearby stars for the small dips caused by transiting planets. TESS matters because nearby stars are easier to study again. When a planet is found around a bright star, other telescopes can follow it. They can measure its mass. They can study its atmosphere. They can ask whether the world is rocky, gaseous, hot, cold, dense, or light. A discovery is only the beginning. First, a telescope notices a dimming. Then scientists confirm that the signal is really a planet. After that, the planet becomes a target for deeper questions. How large is it? How much heat does it receive? Does it have air? Could its atmosphere contain water vapor, carbon dioxide, methane, or other molecules? TESS does not give all the answers at once. It makes a map of possibilities. It finds worlds close enough, bright enough, or interesting enough for future study. Some are too hot for life as Earth knows it. Some are giant planets. Some are small worlds that invite careful attention. The process is patient. A planet may pass in front of its star for only a few hours. Then it disappears into ordinary light until the next orbit. A nearby star dims softly, and another hidden world steps forward. A planet's atmosphere can become a quiet message. When a planet passes in front of its star, a little starlight filters through the planet's atmosphere. That air, if the planet has any, absorbs certain colors of light. Scientists can spread the starlight into a spectrum and look for those missing colors. This method is called transmission spectroscopy. It is one of the gentlest tools in the search for life. It does not see oceans directly. It does not see trees, animals, cities, or clouds in sharp detail. It reads a thin ring of air around a distant world. Different molecules leave different marks. Water vapor, carbon dioxide, methane, oxygen, and ozone can all shape light in their own ways. By studying these patterns, scientists can begin to understand what an atmosphere is made of. But a single molecule is rarely enough. Methane can come from living things, but it can also come from geology. Oxygen can come from photosynthesis, but under some conditions, it can also build up without life. The universe is subtle. Chemistry can imitate simple signs. That is why scientists look for combinations. They ask whether certain gases appear together in a way that is hard to explain without active renewal. They study the planet's star, temperature, orbit, and possible surface conditions. A biosignature is not a simple label. It is a careful clue. The search is slow because the answer matters. Somewhere, a thin atmosphere may hold the first whisper of another living world. The first life found beyond Earth may be very small. When people imagine alien life, they often picture intelligent beings. They imagine voices, signals, machines, or civilizations under strange skies. But the first life discovered beyond Earth may be much simpler. It may be microbial. On Earth, microbes appeared long before plants, animals, or humans. For most of Earth's history, life was microscopic. It lived in oceans, rocks, mats, mud, and deep places. It changed the planet slowly, molecule by molecule, until the atmosphere itself became different. Microbial life is also easier to imagine in harsh environments. A microbe can live where larger creatures cannot. Some survive in boiling springs, some live in salty lakes, some rest inside rocks, some remain active beneath ice, some use chemical energy instead of sunlight. This matters for Mars, Europa, Enceladus, and perhaps many distant planets. If life exists elsewhere, it may not stand on a surface and look at the stars. It may drift in a dark ocean. It may cling to minerals near warm vents. It may sleep beneath frozen soil. It may be too small to see without instruments. Yet such a discovery would be enormous. One living microbe beyond Earth would prove that life is not limited to this planet. It would show that biology can begin in more than one place. The smallest life could carry the largest answer. Mars keeps the memory of ancient water. Mars is dry and cold today, but its surface tells a softer story from long ago. Spacecraft have seen dry river valleys, ancient lake beds, minerals shaped by water, and deltas where streams once carried sediment. These features suggest that Mars once had a warmer, wetter past. This makes Mars one of the most important worlds in the search for past life. If microbes ever lived there, they may have left signs in ancient rocks. These signs would be subtle. They might be organic molecules, mineral patterns, or textures that formed in quiet lake mud billions of years ago. Rovers explore Mars slowly. They move across the ground like patient geologists. They photograph stones, drill samples, study dust, and examine layers of rock. Each layer is a page from an older planet. Each sample may hold part of a vanished environment. Mars does not need to be alive today to matter. Its past may still answer something profound. If life began there independently, then life may be more common than Earth alone suggests. If Mars was habitable but never alive, that would also teach something important. It would show that the right conditions may not always be enough. Either way, Mars helps frame the question with care. A red desert keeps the memory of rivers, lakes, and time. Europa hides an ocean beneath its ice. Europa, one of Jupiter's moons, is covered by a bright icy shell. Across its surface run long lines and cracks, as if the moon has been gently pulled and reshaped. Beneath that ice, scientists think a global ocean may exist. Europa is warmed by tides. As it orbits Jupiter, the giant planet's gravity stretches and squeezes the moon. This motion creates heat inside Europa. That heat may help keep water liquid beneath the frozen crust. This is a different kind of possible home for life. It is not a sunny shore. It is not a blue sky above waves. It is an ocean sealed under ice, far from the sun, moving in darkness. Yet darkness is not empty. On Earth, life thrives near deep sea vents, where chemical energy rises from the seafloor. Europa may have water, energy, and chemistry. It may have an ocean touching rock. These are important ingredients. They do not prove life exists there. They simply make Europa one of the most interesting places to study. NASA's Europa Clipper mission is designed to explore this moon from orbit around Jupiter. It will make many close flybys of Europa, studying its ice, surface chemistry, gravity, magnetic environment, and possible ocean. A moon can look frozen and still from far away. Beneath the quiet ice, a hidden sea may be moving. Enceladus sends pieces of its hidden ocean into space. Enceladus is a small icy moon of Saturn. It is bright, cold, and covered in clean white ice. At first glance, it looks quiet and frozen, but near its south pole, Great plumes rise from long cracks in the surface. These plumes spray water vapor, icy grains, and other materials into space. This is one of the most beautiful gifts in planetary science. A hidden ocean is usually difficult to study. It may lie beneath miles of ice. It may be sealed away in darkness. But Enceladus releases samples of its inner sea naturally, like a moon gently breathing into space. NASA's Cassini spacecraft flew through these plumes during its long mission at Saturn. Its instruments found water, salts, organic molecules, and signs that the ocean may interact with warm rock below. Organic molecules do not prove life. They are simply carbon-rich chemistry, the kind of chemistry life uses on Earth. Still, Enceladus has become deeply important. It may contain liquid water, chemical energy, and a rocky seafloor. These are three ingredients scientists often think about when they imagine habitable environments. The moon is small, but its meaning is large. It shows that even distant icy worlds can be active inside. It shows that oceans may hide far from sunlight. It shows that the outer solar system is not only cold and still. A tiny moon near Saturn opens its ocean to the stars. Titan carries lakes beneath an orange sky. Titan is Saturn's largest moon, and it is one of the strangest familiar places in the solar system. It has a thick atmosphere, soft orange haze, dunes, clouds, rivers and lakes. In some ways it resembles Earth. In other ways, it is deeply different. Titan's surface is far too cold for liquid water to flow in rivers. Instead, methane and ethane can exist as liquids. They fall as rain, gather in lakes, carve channels, and evaporate back into the sky. Titan has a kind of weather, but its weather is made from hydrocarbons. This makes Titan feel like a natural laboratory. It is not a second Earth. It is a world where chemistry has taken another path. Sunlight and charged particles work on methane and nitrogen high in the atmosphere. They create complex organic molecules, which drift downward through the haze and settle onto the surface. Organic chemistry matters because life on Earth is built from carbon chemistry. But organic molecules are not the same as living things. Titan may show how complex chemistry develops before life. It may help scientists understand some of the early steps that could happen on young worlds. NASA's Dragonfly mission is designed to explore Titan with a flying rotorcraft. Titan's thick air and low gravity make flight easier than on many other worlds. Dragonfly will move from place to place, studying the surface and its chemistry. Under Titan's amber sky, chemistry falls softly like weather. Titan may also hide an ocean beneath its ice. The surface of Titan is famous for methane lakes and orange haze. But deep below the frozen crust, there may be something more familiar, a water ocean. Many icy moons in the outer solar system are thought to contain buried oceans, warmed by internal heat and protected by ice. If Titan has an underground ocean, it becomes a world of layers. On top, there are dunes, lakes, and hydrocarbon rain. Beneath that, there may be ice. Deeper still, there may be liquid water mixed with salts or ammonia. The moon may hold two very different kinds of chemistry at once. This layered nature makes Titan especially interesting. Its surface may preserve complex organic molecules. Its interior may contain water. Impacts or geological processes might sometimes mix materials from the surface with water below. Scientists study these possibilities carefully, because prebiotic chemistry often depends on contact between different ingredients. Titan does not need to be alive to be valuable. It may show how chemistry organizes itself in cold conditions. It may show how organic molecules collect, change, and survive over long periods. It may also help explain what early Earth chemistry may have been like before biology became dominant. The search for life is not only about finding life, it is also about learning how nature prepares the ground for life. Titan rests quietly in Saturn's distance, holding many kinds of chemistry in one moon. Life on Earth survives in hidden places. For a long time, people imagined life needed mild conditions. Warm sunlight, open air, fresh water, and a gentle surface seemed necessary. Earth has slowly taught a wider lesson. Life is far more patient and flexible than that. Microbes live in hot springs where water steams from the ground. They live in salty lakes, acidic pools, deep caves, frozen soils, and rocks far beneath the surface. Some live near hydrothermal vents on the ocean floor, where sunlight never reaches. There, chemical energy rises from the planet itself. These organisms are called extremophiles. The word sounds strong, but the idea is quiet. Extremophiles show that life can adapt to places once considered too difficult. They do not make every environment habitable. They simply widen the imagination. This matters for other worlds. If life can live deep underground on Earth, then Mars may have had protected spaces beneath its surface. If life can live near vents in Earth's dark ocean, then Europa or Enceladus may be worth studying carefully. If microbes can survive cold, salt, darkness, or pressure, then alien life may not need to resemble surface life at all. The first life found beyond Earth may be hidden. It may not live under open skies. It may not need sunlight. It may rest in rock, ice, brine, or darkness. Life does not always announce itself with forests and birdsong. Sometimes it continues as a tiny glow inside stone. Deep-sea vents show how life can live without sunlight. At the bottom of Earth's oceans, sunlight disappears. The water is dark, cold, and under enormous pressure. Yet around hydrothermal vents, life gathers in rich communities. Warm mineral-filled water rises from the seafloor. Microbes use chemical reactions for energy. Larger animals depend on those microbes. This is one of the most important lessons for astrobiology. It shows that sunlight is not the only possible energy source for ecosystems. A world with no bright surface may still have useful energy below. If water meets warm rock, chemistry can happen. If chemistry provides energy, life may have a doorway. Hydrothermal vents also matter, because they may resemble places where life began on Earth. Some origin of life theories suggest that early biology could have emerged near mineral-rich vents. These environments provide natural compartments, chemical gradients, heat, and flowing water. They bring together many useful ingredients. No one knows exactly where life began on Earth. It may have started in shallow pools, near vents, in ice, in sediments, or through several connected environments. But vents remain powerful examples. They show how geology and chemistry can support living systems without sunlight. That idea travels easily to icy moons. Europa and Enceladus may have oceans touching rock. If their seafloors are active, they may host chemical energy. The comparison is not proof. It is a reason to keep looking. In the deep ocean, Earth whispers that darkness can still be alive. The origin of life is still an open question. Life exists on Earth, but its first beginning remains one of science's great quiet mysteries. At some point, chemistry became biology. Molecules began to store information, make copies, use energy, and form boundaries. Simple reactions became organized systems. This change is called abiogenesis. It does not describe one single moment. It describes a long path from non-living chemistry to living cells. That path may have included many small steps. Simple molecules formed. Some joined into longer chains. Some became enclosed in tiny droplets or membranes. Some copied imperfectly. Some combinations lasted longer than others. Scientists study these steps in laboratories. They explore how amino acids, nucleotides, lipids, and other molecules can form under early Earth conditions. They study meteorites, volcanic environments, deep-sea vents, drying ponds, and icy settings. Each environment may explain part of the story. The question matters beyond Earth. If life begins easily when ingredients and conditions are right, then the universe may be filled with simple life. If life requires a rare chain of events, then Earth may be unusual. The origin of life is the bridge between chemistry and the search for neighbors among the stars. There is no final answer yet. That uncertainty is not empty. It is a quiet laboratory, filled with experiments, models, and patient thought. Somewhere in Earth's ancient past, ordinary molecules learned a new kind of order. Organic molecules are common in space. The chemistry of life does not begin only on planets. Many organic molecules form in space itself. They have been found in interstellar clouds, comets, meteorites, and the material around young stars. Carbon chemistry drifts through the galaxy long before planets finish forming. This is a gentle and important fact. The universe is not chemically barren. It makes complex molecules in cold clouds and dusty regions. It carries them inside icy bodies. It delivers them to young planets through impacts. Some meteorites found on Earth contain amino acids and other organic compounds. These molecules are not alive. They do not think, move, breathe, or reproduce. But they are part of the raw material from which life may be built. Their presence suggests that planets do not begin with empty chemistry. They may inherit useful ingredients from the clouds that made their stars. Comets and asteroids may have delivered water and organics to the early Earth. They may have done the same for Mars or other young worlds. Even if life is rare, the building blocks appear to be widespread. This makes the search for life feel more connected. A molecule in a meteorite, a cloud between stars, and a cell on Earth all belong to one long cosmic story. Atoms move from stars to dust, from dust to planets, from planets to oceans, and sometimes into life. The galaxy quietly scatters ingredients before any world knows what they may become. Panspermia asks whether life can travel. Panspermia is the idea that life, or the ingredients of life, might move between worlds. A large impact can blast rocks from a planet into space. Some of those rocks may travel for years, centuries, or much longer before landing on another world. Meteorites from Mars have reached Earth. The gentlest version of this idea focuses on chemistry. Organic molecules can travel inside comets, asteroids, and dust. These materials may seed young planets with useful ingredients. This is not controversial in its broad form. Space does carry chemistry from place to place. The stronger version asks whether living microbes could survive the journey. Some microbes on Earth can endure cold, dryness, radiation, and long dormancy. If shielded inside rock, perhaps simple life could survive travel between nearby worlds. This remains uncertain, but scientists study it carefully. Panspermia does not solve the origin of life. If life came to Earth from somewhere else, it still had to begin somewhere. But the idea changes the shape of the question. Life might not always begin separately on every world. It might sometimes spread, especially between planets in the same system. Mars and Earth exchanged rocks in the early solar system. If life began on one, material could have reached the other. This possibility makes Mars even more interesting. A discovery there would need careful study to know whether it represents a second origin or a shared history. Between worlds, even stone can become a quiet messenger. Red dwarf stars may host many small planets. Red dwarfs are the most common stars in the galaxy. They are smaller, cooler, and dimmer than the Sun. Because they are so common, many potentially habitable planets may orbit them. A world around a red dwarf must orbit close to receive enough warmth for liquid water. This closeness creates both promise and difficulty. A nearby planet may be easier to detect as it crosses its star. Its atmosphere may also be easier to study, but red dwarfs can be active, especially when young. They may release flares and radiation that affect nearby planets. A planet close to a red dwarf may also become tidally locked. One side may always face the star, while the other side remains in darkness. At first, this seems strange, but climate models suggest that an atmosphere or ocean could move heat around the planet. A tidally locked world is not automatically lifeless. It is simply different. Red dwarf systems invite careful thinking. They may be the galaxy's most common planetary homes. They may also challenge atmospheres in ways scientists are still studying. Some may be unsuitable. Others may be stable enough for long periods. Because red dwarfs live for a very long time, their planets may have enormous stretches of time. Time is one of life's quiet ingredients. Chemistry may need patience. Around small red stars, worlds may wait close to a gentle ember. TRAPPIST-1 is a system of 7 rocky worlds. TRAPPIST-1 is a small red dwarf star about 40 light-years away. Around it orbit 7 known planets, all roughly Earth-sized. They are packed close to their star, closer than Mercury is to the Sun. Yet because the star is cool and dim, some of these planets receive amounts of energy that make them interesting for habitability studies. The TRAPPIST-1 system is not a second solar system. It is much smaller and tighter. The planets tug on one another as they orbit, creating a delicate gravitational rhythm. Their years are short. Their skies, if they have skies, would look very different from Earth's. Scientists study TRAPPIST-1 because it offers several rocky planets in one nearby system. The James Webb Space Telescope and other observatories can examine some of these worlds, looking for clues about atmospheres. Some may have lost their air, some may have retained it, some may be dry, hot, frozen, or more complex than first imagined. The important point is not that TRAPPIST-1 is alive. There is no evidence of life there. Its importance is that it gives science a real set of rocky exoplanets to compare. It helps researchers learn how small planets around red dwarfs behave. 7 little worlds circle a faint red star, like quiet beads of stone in the dark. The search is becoming more careful, not simply more hopeful. As more planets are discovered, scientists become more cautious. Early excitement is natural, but careful science asks slower questions. Is the signal real? Is the planet truly rocky? Does it have an atmosphere? Could the atmosphere survive its star? Are possible biosignatures actually caused by life or by ordinary chemistry? This caution is not cold, it is protective. A true discovery of life beyond Earth would be one of the deepest discoveries in human history. It must be strong enough to last. Every claim needs careful checking. Every unusual signal needs other explanations tested. The search for life is therefore both imaginative and disciplined. It imagines oceans under ice, microbes under rocks, and atmospheres around distant planets. Then it returns to data. It measures, it compares, it waits. This balance gives the field its quiet beauty. Wonder opens the door, and evidence decides where to step. A world can be interesting without being alive. A molecule can be important without being proof. A silence can be meaningful without being final. In that patience, the question becomes more peaceful. The universe does not need to be rushed to be full of possibility. The James Webb Space Telescope reads the air of distant worlds. The James Webb Space Telescope does not travel to exoplanets. It does not see their surfaces in sharp detail. It does something more delicate. It gathers light, spreads it into colors, and looks for the fingerprints of molecules. When a planet passes in front of its star, some starlight filters through the planet's atmosphere. Each molecule absorbs certain wavelengths. Water vapor leaves one kind of pattern. Carbon dioxide leaves another. Methane, oxygen, ozone, and other gases shape the light in their own quiet ways. This is called spectroscopy. It turns light into a message. A distant planet may be too far away to visit, but its air can still leave marks in starlight. Those marks may reveal whether the planet has an atmosphere, what that atmosphere contains, and whether clouds or hazes float there. The work is difficult. A planet is tiny beside its star. Its atmosphere is thinner still. The signal can be faint, mixed with noise, and shaped by the star itself. Scientists must observe carefully, compare models, and repeat measurements when possible. Webb is especially useful because it sees infrared light. Many molecules leave strong patterns there. This helps researchers study planets that earlier telescopes could not examine in the same detail. A planet's atmosphere is not a voice, but it is not silent either. In a soft ribbon of light, a faraway world can begin to describe itself. A biosignature is a clue, not a final answer. A biosignature is something that might be produced by life. It may be a gas in an atmosphere, a chemical pattern in a rock, a color on a surface, or a structure made by living organisms. On Earth, life has changed the planet in many ways. It fills the air with oxygen. It shapes soils. It builds shells, mats, forests, reefs, and microscopic patterns in stone. But science treats biosignatures carefully. A possible sign of life is not the same as proof. Nature can produce surprising chemistry. Without biology, volcanoes can release gases. Sunlight can split molecules apart. Rocks can react with water. Atmospheres can change over time. This is why a biosignature must be studied in context. The planet's star matters. Its temperature matters. Its atmosphere matters. Its geology, orbit, age, and radiation environment all matter. A gas that seems meaningful on one planet may have a different explanation on another. The most useful signs may come from combinations. Oxygen and methane together, for example, can be interesting because they tend to react with each other. If both remain present in large amounts, something may be renewing them. On Earth, life helps do that. But even then, caution is needed. The search for biosignatures is like reading a poem in a language only partly known. One word is not enough. The whole sentence must be understood. Life may leave marks, but wisdom asks science to read them slowly. Oxygen became Earth's great visible sign. Today, Earth's atmosphere contains a large amount of oxygen. This oxygen is strongly linked to life. Plants, algae, and cyanobacteria use photosynthesis. They take in carbon dioxide and water, use sunlight, and release oxygen. Over long ages, this changed the planet. But early Earth did not always have oxygen-rich air. For a long time, life existed mostly as microbes in low-oxygen environments. Then cyanobacteria helped release oxygen into the oceans and atmosphere. This gradual transformation is often called the Great Oxidation Event. From far away, oxygen might make Earth look unusual. It is a reactive gas. It combines with many materials. If it stays abundant, something must help maintain it. On modern Earth, biology does much of that work. Still, oxygen is not always simple. There are ways oxygen or ozone could build up on some planets without life, especially under unusual conditions. A planet around an active star might lose water, leaving oxygen behind. Chemical processes can create misleading signs. This makes oxygen powerful, but not perfect. It is one of the great clues, not a single answer. Scientists search for the full story around it. Water vapor, methane, carbon dioxide, clouds, temperature, surface pressure, and the nature of the star. Earth teaches both hope and caution. A living world can fill its sky with oxygen, but the sky must still be read with care. Methane is a small molecule with a wide story. Methane is made from carbon and hydrogen. On Earth, it comes from many sources. Some are biological. Microbes produce methane in wetlands, animal stomachs, sediments, and oxygen-poor environments. Some sources are geological. Methane can form through reactions involving rocks, water, and heat. Because of this, methane is both interesting and difficult. If methane appears in the atmosphere of another world, it may invite attention, but it cannot stand alone as proof of life. It must be understood beside the planet's other gases and conditions. On Mars, methane has been especially debated. Some measurements have suggested small amounts or changing levels. Other measurements have not found the same patterns. This makes the question complicated. Methane on Mars, if present, could come from geology, chemistry, or perhaps biology. No confirmed biological source is known. On exoplanets, methane may be part of an atmospheric puzzle. It could appear with carbon dioxide, water vapor, oxygen, or other molecules. It may help scientists understand temperature, chemistry, and possible energy flows. Methane is simple in shape but rich in meaning. A few atoms joined together can open many possible stories. Some stories are living, some are not. The task is to listen without rushing. In the quiet chemistry of a planet's air, one small molecule can carry many paths. A living planet may be out of balance. One way to think about life is through disequilibrium. This means a system contains chemicals that should not remain together for long unless something keeps renewing them. Earth's atmosphere is out of balance in this way. Oxygen and methane exist together. Even though they react over time, life helps maintain this imbalance. Plants and microbes release gases. Other organisms consume them. Oceans absorb and exchange materials. Rocks weather. Volcanoes release new compounds. The planet becomes a moving system, always changing, always restoring certain patterns. A dead world can also be chemically active. Volcanoes, sunlight, impacts, and oceans can all change atmospheres. But life adds another layer. It takes energy from sunlight or chemistry and uses it to build order. It can keep pushing an environment away from simple balance. This is why scientists often search for atmospheric combinations instead of single gases. A planet with oxygen alone may be interesting. A planet with oxygen, methane, water vapor, and a stable climate may be more interesting. The whole pattern matters. The idea is subtle and beautiful. Life may not shout across space. It may simply keep a planet from settling into chemical stillness. A living world may be recognized by the gentle tension in its air. Clouds can hide and reveal distant worlds. Clouds are familiar on Earth. They soften sunlight, carry water, reflect heat, and shape weather. On exoplanets, clouds may also be important, but they can make atmospheres harder to study. A thick cloud deck can flatten a spectrum, hiding the molecular patterns below. Some exoplanets may have water clouds. Others may have clouds made of minerals, salts, metals, or exotic hazes. Hot planets can have silicate clouds. Cooler planets may hold different kinds of particles. Around small red stars, hazes may form through complex reactions driven by starlight. Clouds complicate the search for life, but they also make planets more real. A cloud is not just an obstacle. It is part of a world's climate. It tells a story about temperature, pressure, chemistry, and circulation. It may help protect a surface, reflect harmful radiation, or trap warmth. On Earth, clouds are part of the living planet's rhythm. They gather over oceans, drift across continents, and return water to land. On another world, clouds may move through a sky no eye has seen. They may cover oceans, deserts, ice, or rock. A cloudy spectrum may seem quiet, but even quietness gives information. It may suggest high-altitude haze, thick vapor, or reflective particles. It may tell scientists where to look again. Even when clouds hide a world, they do so with their own soft language. Red dwarf planets may live under restless skies. Many promising exoplanets orbit red dwarf stars. These stars are small and cool, so their habitable zones lie close in. A planet there may receive enough warmth for liquid water, but it also lives near its star's activity. Young red dwarfs can flare. They can release bursts of radiation and charged particles. These events may affect atmospheres, especially on planets orbiting very close. A world might lose air over time, or its chemistry might be changed by high-energy light. This does not mean all red dwarf planets are lifeless. It means they must be studied carefully. Some may have strong magnetic fields. Some may have thick atmospheres. Some may begin with enough gases or water to survive early activity. Some stars may calm with age, giving planets long quiet eras afterward. Red dwarfs live for extremely long times. Some may shine for trillions of years, far longer than the Sun. If a planet can keep its atmosphere and water through the difficult early period, it may have vast amounts of time for chemistry to unfold. The contrast is gentle and deep. Around small stars, worlds may face restless beginnings and long, patient futures. Habitability becomes a story, not a simple location. A red dwarf's light may be dim, but its planets ask bright questions. The search for alien plants begins with color. On Earth, plants use chlorophyll to capture sunlight. They reflect more strongly in near-infrared light, creating what scientists call the vegetation red edge. From far away, this change in reflectance could be a sign of widespread photosynthetic life. This idea is fascinating, but difficult. A planet would need enough plant-like life, covering enough surface to affect its reflected light. The telescope would need to separate the planet's light from its star. Clouds, oceans, deserts, ice, and seasons would all shape the signal. Alien photosynthesis might not use the same colors as Earth plants. It would depend on the star's light and the chemistry available. Around a red dwarf, living pigments might adapt to different wavelengths. Around a brighter star, they might need more protection. A living surface could be green, dark, red, purple, or something unfamiliar. Scientists do not search only for forests like Earth's. They search for patterns that could show biological use of light. They compare possible life signals with non-living surfaces, minerals, ice, and atmospheric effects. The idea is wonderfully quiet. A distant world might not send a signal. It might simply reflect starlight in a way that suggests something is harvesting energy. Somewhere, under another sun, life may show itself as a subtle color on a turning world. Technosignatures search for signs of technology. Biosignatures look for life in general. Technosignatures look for technology. A technosignature could be a radio signal, a laser pulse, unusual atmospheric chemicals, artificial lights, waste heat, or another sign that a civilization has changed its environment. This search is different from looking for microbes. Microbes may be common but quiet. Technology might be rare, but more visible across distance. A civilization could intentionally transmit signals, or it might unintentionally leak energy into space. It might build large structures, use powerful communication systems, or alter its planet in ways that telescopes could notice. Radio SETI is the most famous version. Radio waves travel well through space. They can cross enormous distances. A narrowband radio signal, if found from a cosmic direction and confirmed as artificial, would be unlike most natural sources. But the search is difficult. The galaxy is vast. Signals may be weak. They may be brief. They may be aimed somewhere else. Civilizations may use technologies humans do not expect. They may choose silence, or communicate in ways that do not look like signals at all. So far, no confirmed technosignature has been found. Still, the search continues. because the question is too meaningful to ignore. In the soft noise of the cosmos, science listens for a pattern that nature did not make. The wow signal remains a famous mystery, not an answer. In 1977, a radio telescope detected a strong narrowband signal that became known as the wow signal. It lasted for a short time and seemed unusual enough that astronomer Jerry Amon marked the data with the word wow. The name remained. The signal has become part of the public imagination. It feels like the kind of event people expect in the search for extraterrestrial intelligence. A brief signal, a quiet telescope, a strange mark in the data, but scientifically, it remains unconfirmed. It was not detected again in the same way. Without repetition, it cannot be accepted as evidence of alien technology. This is an important lesson. In SETI, a signal must be checked carefully. It must be separated from Earth-based interference, satellites, aircraft, natural sources, instrument effects, and random noise. A true extraterrestrial signal would need independent confirmation. The wow signal is valuable because it shows both excitement and caution. It reminds the search to stay open, but not careless. It also shows how patient the work must be. A single strange moment can inspire decades of thought, but evidence must return before certainty can arrive. The universe can offer mysteries without offering conclusions. Some signals remain like quiet footprints that never quite become a path. Radio telescopes listen across enormous silence. A radio telescope can be a great dish, an array of antennas, or a network spread across wide land. It gathers radio waves from space, focusing faint signals that human ears could never hear directly. Pulsars, galaxies, gas clouds, planets, and human technology all create radio noise. SETI searches within this ocean of signals. Scientists look for patterns that seem artificial. A very narrow frequency can be interesting, because many natural sources are broader. Repetition can be important. Direction matters too. A signal from one fixed point in the sky is more interesting than one that follows an Earth satellite. The challenge is immense. Human civilization itself fills the radio environment with interference. Phones, satellites, aircraft, radar, and electronics can all create signals. Many candidate signals eventually turn out to be local. This does not make the search less important. It makes careful filtering essential. Listening to space is like sitting beside a vast dark sea. Most sounds are waves, wind, and the creaking of the shore. But the listener remains patient, because one clear pattern would change everything. Radio telescopes do not expect the universe to be easy. They simply keep listening, calmly and carefully, across the dark. Silence does not mean emptiness. So far, Earth has not received a confirmed message from another civilization. The sky has not answered in a way science can verify. This silence can feel large, but it does not prove the galaxy is empty. There are many reasons a civilization might not be heard. It may be too far away. Its signals may be too weak. It may not use radio for long. It may communicate through methods humans have not imagined. It may exist at a different time, rising and fading millions of years before or after humanity listens. The Milky Way is about 100,000 light-years across. Even light needs time to cross it. A message sent from one side may take tens of thousands of years to arrive. A reply would take just as long. Communication across a galaxy is not like conversation across a room. It is more like exchanging letters with deep time. The silence may also come from the youth of the search. Radio astronomy has existed for only a small moment compared with the age of the galaxy. Humans have looked carefully for a very short time. The listening window is still narrow. Silence, in science, can be a beginning. It sets limits. It shapes better searches. It teaches humility. The stars may be quiet, but quiet is not the same as empty. The Fermi Paradox asks why the galaxy seems so quiet. The Milky Way contains hundreds of billions of stars. Many of those stars may have planets. Some planets may be rocky. Some may orbit in places where liquid water could exist. With so many possible worlds, one question naturally rises. If life can appear elsewhere, why has no confirmed civilization been found? This question is often called the Fermi Paradox. It is named after physicist Enrico Fermi, who wondered why there was no obvious sign of extraterrestrial intelligence. The question is simple on the surface, but it opens into many quiet possibilities. Maybe simple life is common, but complex life is rare. Maybe complex life appears, but intelligence is unusual. Maybe intelligence appears, but technology lasts only briefly. Maybe civilizations do not send signals. Maybe they send signals in ways humans do not understand. Maybe the distances are simply too large, and the timing never lines up. The galaxy is not only wide, it is old. A civilization could have risen and faded millions of years before humans learned to listen. Another could begin millions of years after Earth grows quiet. Two living worlds may share the same galaxy and never share the same moment. The Fermi Paradox is not a final answer. It is a calm doorway into uncertainty. It reminds science that possibility and evidence are not the same thing. The stars may be many, and the silence may still be deep. The Great Filter is one possible explanation. The Great Filter is an idea that tries to explain why advanced civilizations are not obvious in the galaxy. It suggests that somewhere between simple chemistry and galaxy-wide technology, there may be a very difficult step. Many worlds may never pass it. That difficult step could be behind Earth. Perhaps the origin of life is extremely rare. If so, Earth has already crossed the hardest bridge. The universe may have many planets, but only a few ever become alive. In that case, even simple microbes would be precious. The filter could also be later. Perhaps single-celled life appears often, but complex cells are rare. On Earth, simple life existed for billions of years before large animals appeared. That long delay may mean complexity is not easy. The filter could be intelligence, technology, long-term stability, or the ability to survive planetary changes. A civilization may discover powerful tools before it learns wisdom. It may change its climate, exhaust resources, or become unable to continue. This idea can sound heavy, but in a calm science journey, it becomes a reminder of tenderness. Life is not guaranteed to climb every step. A living planet is not just interesting, it is delicate. Its future depends on countless balances. The Great Filter does not tell science which step is hardest. It only gives the question a shape. Somewhere between dust and the stars, life may face a very narrow bridge. Earth took a long time to become complex. The age of Earth is about 4.5 billion years. Life appeared early in the planet's history, at least in microbial form, but complex animals came much later. For most of Earth's life story, the planet belonged to microbes. This long microbial age matters. It shows that life and complex life are not the same question. A planet may become alive and still remain simple for billions of years. Its oceans may hold microbes. Its rocks may hold chemical traces. Its atmosphere may change slowly, but no eyes may open. No voices may rise. No tools may be made. Complex cells, called eukaryotic cells, were a major step. They contain internal structures, including a nucleus and energy-producing mitochondria. Their origin involved deep biological changes, possibly including one cell living inside another. This step may have been rare or difficult. After complex cells appeared, multicellular life still needed time. Large animals came later. Land plants came later. Intelligence capable of radio astronomy came much later still. Human technology occupies only a tiny final moment of Earth's long history. This does not mean intelligence is impossible elsewhere. It simply shows that the path can be slow. The universe may contain many living planets where life remains microscopic, patient, and hidden. A world can be alive for ages before it ever looks up at the stars. The Cambrian explosion shows how sudden complexity can seem. More than 500 million years ago, many animal groups appeared in the fossil record over a relatively short geological period. This event is often called the Cambrian explosion. It was not an explosion in a fiery sense. It was a flowering of forms, shells, eyes, limbs, mouths, bodies, and new ways of living. Before this, life had already existed for billions of years. Microbes had shaped the oceans and atmosphere. Simple multicellular organisms had appeared. The Cambrian did not come from nowhere. It came after long preparation. Still, it shows something important about life's timing. For ages, a planet may seem biologically quiet from far away. Then, under the right conditions, complexity may diversify. New body plans may appear. Predators and prey may shape evolution. Eyes may change the rhythm of life, because seeing and being seen create new pressures. This matters for the search beyond Earth. A planet may sit in a long, simple phase. It may not have large creatures, but it may still be biologically rich. Another planet may pass through a rapid period of diversification if oxygen, ecology, and evolution allow it. The Cambrian explosion also reminds science not to judge a planet too quickly. Life's outward appearance changes across time. A living world may look very different at different ages. For billions of years, Earth prepared quietly before complex life unfolded. Intelligence is only one branch of life's tree. Humans often search for intelligence because humans are intelligent. They build telescopes, send spacecraft, and wonder about minds beyond Earth. But life on Earth shows that intelligence is not the only success. Bacteria, trees, fungi, insects, fish, and birds all continue in their own ways. Evolution does not aim directly at technology. It responds to environments. It shapes organisms to survive, reproduce, and fit their surroundings. Intelligence can help, but it is not always necessary. A microbe can thrive for billions of years without a brain. A forest can transform a planet without building a radio. This is important when thinking about alien life. A living world may never produce a technological species. It may have oceans full of simple organisms. It may have plants and animals, but no machines. It may have intelligence expressed in ways that do not lead to signals. On Earth, several animals show remarkable intelligence. Dolphins, elephants, crows, octopuses, apes, and whales all reveal memory, problem-solving, communication, or social complexity. Yet only one species builds radio telescopes. Technology depends on many things: bodies, environments, materials, social learning, energy use, and time. Alien life may be intelligent in a way that never becomes visible across space. A mind can exist beneath a sky and leave no signal among the stars. Civilizations may be separated by time. The galaxy is ancient. The Milky Way formed billions of years before the Sun. Many stars are older than Earth. Many planets may have formed before the solar system existed. If life can appear elsewhere, some worlds may have had a head start of millions or billions of years. This makes the silence more mysterious, but also more delicate. A civilization might not last long in a detectable state. It may use radio for a few centuries, then move to quieter technologies. It may become inward-looking. It may decline. It may transform into something no longer visible to us. Another civilization may arise after humanity is gone. It may look at the sky and find no signal from Earth. The two civilizations may share the same galaxy but never overlap. Time becomes another kind of distance. Even on Earth, radio leakage into space is very recent. The period in which humans have been strongly detectable by radio is tiny compared with geological time. A passing civilization would need to be looking in the right way, at the right moment, from the right distance. This thought softens the question. The galaxy may not be empty. It may simply be unsynchronized. Life may rise in scattered moments, like fireflies blinking across a vast summer field, rarely flashing together. Across cosmic time, even neighbors can miss each other completely. Distance makes conversation very slow. Light is the fastest thing in the universe, but space is immense. The nearest star system, Alpha Centauri, is more than 4 light-years away. A message sent there would take more than 4 years to arrive. A reply would take more than 4 years to return. That is the nearest system. Many interesting stars are tens, hundreds, or thousands of light-years away. A message to a world 1,000 light-years away would arrive 1,000 years later. A reply would need another 1,000 years. A conversation would become a structure built from centuries. This changes the meaning of contact. Human communication feels immediate because Earth is small. Voices cross rooms. Signals cross oceans. Messages cross the planet in moments. But between stars, even light becomes slow. A civilization might hear a signal from Earth long after it was sent. It might answer kindly, and humanity would not know for generations. Or a signal might arrive from a civilization that no longer exists. The message would still be real, but the sender would belong to the past. The search for life is also a search through time. Telescopes see stars as they were when their light began traveling. SETI listens not only across space but across history. A message between stars is less like a phone call and more like a bottle drifting across an ocean of years. The Drake equation turns wonder into questions. The Drake equation was created by astronomer Frank Drake as a way to think about the number of communicative civilizations in the galaxy. It does not give a known answer. Instead, it breaks the question into pieces. How many stars form each year? How many have planets? How many planets could support life? How often does life actually begin? How often does intelligence appear? How often does technology become detectable? How long do such civilizations last? Some parts of the equation are now better understood than before. Exoplanet science has shown that planets are common, but other parts remain deeply uncertain. No one knows how often life begins. No one knows how often intelligence develops. No one knows the average lifetime of a technological civilization. The equation is useful because it organizes ignorance. It takes a huge question and divides it into smaller ones. Each mission, telescope, and discovery can improve one piece. Finding more Earth-sized planets helps. Studying atmospheres helps. Understanding the origin of life helps. Searching for signals helps. The Drake equation is not a machine that produces certainty. It is a quiet map of what needs to be learned. It turns the question, are we alone, into a field of smaller lights. Rare Earth theory says complex life may be uncommon. Rare Earth theory suggests that simple life may exist elsewhere, but complex life like animals may be rare. The idea is not that Earth is magical. It is that Earth may have benefited from a special combination of conditions. Earth has a stable, long-lived star. It has liquid water. It has plate tectonics which help recycle carbon and shape climate over deep time. It has a large moon, which may help stabilize its tilt. It has a magnetic field. It has giant planets farther out, which may influence the impact environment. It also avoided certain disasters long enough for complexity to develop. Not every scientist agrees on how important each factor is. Some may be essential, some may be helpful, but not required. Some may matter less than once thought. The theory remains a discussion, not a settled answer. Still, it gives a useful caution. A planet in the habitable zone may not be enough. A rocky surface may not be enough. Life may need stability, chemistry, oceans, and time. Complex life may need even more. The theory also makes Earth feel deeply gentle. It is not simply a planet with life. It is a planet where life remained possible through vast changes. If Earth is rare, then every cloud, leaf, tide, and breath becomes even more precious. The Copernican principle suggests Earth may not be unique. Long ago, people thought Earth stood at the center of the cosmos. Astronomy slowly moved Earth away from that special position. Earth orbits the Sun. The Sun is one star among many. The Milky Way is one galaxy among many. This pattern of humility is sometimes connected to the Copernican principle. The principle suggests that Earth may not occupy a uniquely privileged place. If planets are common, and if the ingredients of life are common, then perhaps life may also be common. Earth may be special to living beings here, but not physically unique in the universe. This idea balances rare Earth theory. One view reminds science that complex conditions may be hard to assemble. The other reminds science that nature often repeats patterns. Stars form by the billions. Planets form by the billions. Organic molecules appear in space. Water is found in many places. The truth may lie somewhere in between. Earth may be ordinary in some ways, and rare in others. Life may be common, while intelligence is uncommon. Microbes may be widespread, while civilizations are very rare. Science does not choose an answer because it feels comforting. It gathers evidence patiently. Earth may be a jewel, and still not the only jewel in the dark. The galaxy may contain many quiet biospheres. A biosphere is the total living system of a world. On Earth, it includes microbes in soil, plankton in oceans, forests on land, fungi underground, animals in motion, and tiny organisms in places humans rarely see. It reaches from deep rock to high clouds. Alien biospheres, if they exist, may be quieter than Earth's. They may be microbial. They may live under ice. They may never produce oxygen-rich air. They may remain hidden below surfaces, invisible to distant telescopes. This possibility is important. A galaxy full of life might still seem silent. Microbes do not build transmitters. Subsurface oceans do not reflect forests into space. A living moon under ice may leave only subtle chemical signs, perhaps in a plume or surface crack. Earth's own biosphere would have looked different across time. For much of its history, there were no plants, no animals, no cities, and no radio signals. Yet Earth was alive. A distant observer might have needed careful instruments to notice. This teaches patience in the search. The most common life in the universe may be small, quiet, and hidden. It may never call out. It may simply continue. A silent galaxy could still be filled with tiny living worlds. A planet may need a stable climate for life to continue. Life may begin during a gentle window, but it also needs time. A planet that changes too quickly may make survival difficult. Oceans can freeze, atmospheres can vanish, surfaces can become too hot or too dry. For life to grow more complex, a world may need long ages of relative stability. Earth has changed many times. It has passed through ice ages, warm periods, asteroid impacts, volcanic events, and shifting continents. Yet through all of this, liquid water remained. The planet bent, but it did not break. Life retreated, adapted, returned, and continued. One important part of this stability is the carbon cycle. Carbon moves between air, oceans, rocks, volcanoes, and living things. When carbon dioxide rises, the planet can warm. When it falls, the planet can cool. Over long periods, weathering rocks can remove carbon dioxide from the air. Volcanoes can return it. This slow exchange helps steady Earth's climate. Other worlds may not have such a balance. A planet with too much carbon dioxide may trap too much heat. A planet with too little may freeze. A world without active geology may lose the ability to adjust across deep time. Habitability is not only about a planet's position around its star, it is also about the planet's ability to remain gentle enough for long enough. A living world may be a world that learns to keep its warmth softly balanced. Plate tectonics may help a planet breathe. Earth's outer shell is divided into moving plates. These plates drift slowly over the softer mantle below. They collide, separate, slide past each other, raise mountains, open oceans, and carry old crust back into the planet's interior. This movement is called plate tectonics. It shapes earthquakes and volcanoes, but it also plays a quiet role in habitability. By recycling carbon between rocks, air, and the deep earth, plate tectonics may help regulate climate over long ages. It also creates many environments where chemistry can happen. Continents weather under rain, minerals react with carbon dioxide, sediments carry carbon into the ocean. Some of that carbon becomes buried and later returns through volcanoes. This is a slow planetary rhythm, almost like a geological breath. Whether plate tectonics is required for complex life remains uncertain. Some planets may regulate climate in other ways. Some may have stagnant lids, where the crust does not break into moving plates, yet still have volcanoes or chemical cycling. Venus, Mars, and Earth show different styles of planetary activity. Still, Earth's plate tectonics gives one example of how a rocky planet can stay dynamic for billions of years. It keeps the surface connected to the deep interior. It renews landscapes. It builds chemical variety. A planet with moving plates is not just a stone in space. It is a world whose surface slowly turns over in its sleep. A magnetic field can help protect an atmosphere. Earth has a magnetic field generated by motion inside its liquid outer core. This field reaches far into space, forming a protective region called the magnetosphere. It helps deflect charged particles from the sun, guiding many of them around the planet. A magnetic field does not make a world perfectly safe. Earth still receives solar particles. Aurorae glow near the poles where charged particles interact with the upper atmosphere. But the field helps reduce atmospheric loss over time, especially when combined with Earth's gravity and thick air. Mars gives an important contrast. It once had a global magnetic field, but that field faded long ago. Today, Mars has only patches of crustal magnetism. Its thin atmosphere has been gradually stripped and altered by solar wind and radiation. This is one reason Mars is now cold and dry at the surface. For exoplanets, magnetic fields are difficult to detect. Scientists often study them indirectly, through models and possible star-planet interactions. A world around an active red dwarf may especially benefit from atmospheric protection, though a magnetic field is only one piece of a larger story. Life may not always need a global magnetic shield. A thick atmosphere, ocean, ice shell, or underground environment can also offer protection. Still, for surface life like Earth's, a magnetic field may be a gentle guardian. Around a living planet, invisible lines can become a quiet shelter. A large moon may help steady a planet's tilt. Earth's moon is unusually large compared with its planet. It raises tides, lights the night, slows Earth's rotation over time, and may help stabilize Earth's axial tilt. That tilt gives Earth its seasons. If the tilt changed wildly, climate patterns could shift in extreme ways. A stable tilt may support long-term climate stability. It helps keep sunlight patterns from changing too dramatically over time. This does not mean every living world needs a large moon. It only means Earth's moon may have helped make Earth's environment more steady. The moon may also have influenced early tidal environments. Tides move water across shorelines. They create wet and dry cycles. Some origin of life ideas suggest that such cycles could help simple molecules concentrate and react. In this way, the moon may have shaped not only Earth's sky, but Earth's chemistry. Other planets may have moons of their own. Some may be small and distant. Some may be large. Some may tug on oceans, raise tides, or warm interiors. A moon can be more than a companion. It can become part of a planet's habitability. There is no single required design for life. The universe may allow many paths, but Earth's moon shows how a nearby body can gently influence a world for billions of years. A pale moon in the night may be part of why Earth stayed quietly kind. Giant planets can shape a solar system's safety. Jupiter is the largest planet in the solar system. Its gravity is powerful. It shapes asteroid paths, captures some objects, redirects others, and influences the architecture of the outer solar system. For a long time, people imagined Jupiter as a simple shield for Earth. The truth is more complex. Jupiter can protect, but it can also disturb. Its gravity can send some objects away, while sending others inward. Its role depends on the location of asteroids, comets, resonances, and the history of the solar system. Still, giant planets matter. Their positions can affect the number of impacts on rocky worlds. Too many large impacts may make life difficult, especially for complex organisms. Too few impacts may change how water and organics are delivered early in a planet's history. The balance is subtle. In other star systems, giant planets can migrate. They can move inward or outward over time, scattering smaller worlds or pulling material into new orbits. Some systems contain hot Jupiters, giant planets orbiting very close to their stars. Such worlds may have moved through their systems, reshaping everything around them. The arrangement of planets matters as much as the planets themselves. Habitability may depend on a whole system's quiet architecture. A small living world may owe part of its calm to distant giants moving slowly in the dark. Super-Earths may be common, but they remain mysterious. A super-Earth is a planet larger than Earth but smaller than Neptune. The name does not mean it is better than Earth. It only describes size. These planets are common around other stars, even though the solar system has no true example. Some super-Earths may be rocky. Others may have thick atmospheres, deep oceans, or layers of gas and ice. Size alone does not reveal their nature. A planet twice Earth's radius may not be a larger Earth at all. It may be more like a small Neptune, wrapped in a thick envelope of hydrogen and helium. This makes super-Earths both exciting and difficult. If a rocky super-Earth has a stable atmosphere and surface water, it could be an interesting place for habitability. Its stronger gravity might hold air well. Its geology might remain active longer, but too much atmosphere could create crushing pressure or strong greenhouse heating. Scientists study mass and radius together to estimate density. A dense planet is more likely rocky. A lighter planet may contain gases or ices. Even then, many possibilities remain. Atmospheres, interiors, oceans, and clouds can make worlds complicated. Super-Earths remind science that the universe does not copy the solar system exactly. It creates planet types that feel familiar and unfamiliar at the same time. Between Earth and Neptune, many quiet worlds wait for clearer names. Ocean planets may be covered almost entirely in water. Some exoplanets may contain far more water than Earth. They may have deep global oceans with little or no exposed land. These are sometimes called ocean worlds or water worlds. Their surfaces, if warm enough, could be wrapped in endless seas beneath thick atmospheres. At first, an ocean planet sounds like a perfect home for life. Water is present everywhere. The climate may be gentle. Chemistry can move through the sea, but habitability is still complex. If the ocean is extremely deep, high pressure may create layers of exotic ice at the bottom. This ice could separate liquid water from the rocky interior. That separation may matter. On Earth, the interaction between water and rock provides important minerals and chemical energy. Weathering continents also helps regulate carbon dioxide. A planet with no land may have different cycles. It may still be habitable, but not in the same way Earth is. Some ocean worlds may have active seafloors. Others may be sealed away from rock. Some may lose water to space. Others may keep it for billions of years. A water-rich planet is not automatically alive, but it is deeply worth studying. The idea expands the imagination. Earth's oceans are large, yet they cover only part of the planet. Somewhere, there may be worlds where no continent breaks the horizon. A whole planet may turn beneath its star as one vast, dark blue sea. Rogue planets drift without a star. Not every planet orbits a sun. Some planets may be ejected from their birth systems by gravitational interactions. Others may form alone in clouds of gas and dust. These objects are called rogue planets, free-floating planets, or wandering planets. At first, a planet without a star seems unlikely to support life. Without starlight, its surface would be cold and dark. Any oceans would freeze. Photosynthesis, as Earth knows it, would not be possible. Yet some scientists still think about hidden possibilities. A rogue planet with a thick atmosphere might trap internal heat. A planet with a deep ocean under ice might keep liquid water below, warmed by radioactive decay or leftover heat from formation. A large rogue world with moons might create tidal heating. Life, if possible there, would likely depend on chemical energy, not sunlight. These ideas remain speculative. No known rogue planet is known to host life, but they show how wide the concept of habitability can become. A world does not always need a sunrise to have warmth somewhere inside. Rogue planets also remind science that the galaxy contains more than shining stars and orderly systems. Some worlds wander through the dark alone, carrying their histories with them. A planet can lose its sun and still keep a secret warmth deep below. White dwarf stars may have quiet habitable zones. A white dwarf is the dense remnant left after a sun-like star finishes its main life. It is small, hot at first, and slowly cooling over billions of years. Around such a star, a habitable zone would lie very close in, because the star gives off much less light than it once did. This idea is unusual. A planet near a white dwarf would have survived a dramatic stellar history. When the original star became a red giant, it may have swallowed or scorched inner planets. Later, remaining planets, asteroids, or moons could shift into new orbits. Some worlds might form or settle closer after the star becomes a white dwarf. If a rocky planet existed in the right place, it might receive gentle warmth for a time. Its atmosphere could, in theory, be studied by transit methods. Because a white dwarf is so small, a planet crossing in front of it would block a relatively large fraction of its light. But white dwarf habitability is uncertain. The path to such a stable planet may be difficult. Radiation, tidal forces, and past stellar changes matter. Still, the idea shows how life searches reach beyond ordinary stars. Even after a star's bright life has ended, a small zone of warmth may remain. A cooling star can still hold a quiet circle of possibility. The galactic habitable zone is a wider idea of home. Habitability may depend not only on a planet and its star, but also on where the system lies in the galaxy. The galactic habitable zone is the idea that some regions of a galaxy may be more favorable for long-term life than others. Near the galactic center, stars are crowded. Supernovae, radiation, and gravitational disturbances may be more common. Far out in the galaxy's edges, heavy elements may be less abundant. Rocky planets need elements like silicon, iron, magnesium, oxygen, and others. These elements are forged by older generations of stars and spread through space. A middle region may offer a softer balance. There may be enough heavy elements to build rocky planets, but not too many dangerous nearby events. The Sun lies in the Milky Way's disk, far from the crowded center, in a region where stable planetary systems can exist. The idea is not exact. Galaxies are complex. Habitable worlds may exist in many regions. Stars move over time. The Milky Way itself has changed across billions of years. But the concept helps science think at larger scales. Life may need a good planet, a steady star, and a calm enough neighborhood. The setting matters, from minerals in a rock to the architecture of a galaxy. Even home can be measured in rings of starlight across the Milky Way. The Sun is a steady star, and that steadiness matters. The Sun is not rare in every way, but it is deeply important to Earth. It has shone with relative stability for billions of years. Its brightness has slowly increased over time, but not so violently that Earth lost its oceans. This long steadiness gave life time to begin, adapt, and become complex. Some stars are larger and shorter-lived. Massive blue stars burn brightly and quickly, ending their lives after only millions of years. That may be too brief for complex life as Earth knows it. Smaller red dwarfs live far longer, but their young activity may challenge nearby planets. The Sun sits between these extremes. A star's lifetime matters because evolution is slow. Earth needed billions of years to produce complex organisms and intelligent technology. A short-lived star may not give planets enough calm time. A very active star may strip atmospheres or bathe close planets in radiation. The Sun also emits the kind of light that supports Earth's photosynthesis. Plants and microbes use sunlight to build sugars and release oxygen. Over ages, this process changed the entire planet. Other stars may support life in other ways, but Earth's story is shaped by the Sun's particular rhythm. A steady star can become a quiet clock for life. The solar system is one example, not the only design. The solar system feels natural because it is home. Small rocky worlds orbit near the Sun. Giant planets orbit farther away. Icy bodies drift in distant regions. Moons, rings, asteroids, comets, and dwarf planets fill the spaces between. But exoplanet discoveries show that other systems can be very different. Some have giant planets close to their stars. Some have rocky planets packed into tight orbits. Some have planets circling two suns. Some have worlds larger than Earth but smaller than Neptune. Some systems may be calm and orderly, while others are tilted, crowded, or reshaped by past migrations. This variety matters for life. The arrangement of planets affects impacts, orbital stability, climates, tides, and the delivery of water. A rocky planet may need a stable orbit for long periods. Too much gravitational disturbance can change seasons or temperatures. Too little movement may make a system quiet, but chemistry still depends on many factors. There may be many possible designs for habitable systems. Earth does not need to be the only template. A moon around a giant planet might be habitable. A tidally locked planet around a red dwarf might be habitable. A deep ocean world might be habitable in a different way. The universe is not a factory making copies of Earth. It is a garden of arrangements, each one turning softly through time. Life may begin with chemistry that learns to copy itself. One of the deepest questions in astrobiology is how non-living chemistry becomes life. A living cell is full of organized systems. It stores information, it uses energy, it builds parts, it repairs itself. It copies instructions and passes them on. But before cells existed, there had to be simpler steps. Many scientists study the idea of self-replicating chemistry. A molecule that helps make copies of itself has a special power. It can become more common. If the copies are not perfect, variation appears. Some versions may last longer, copy better, or work in different conditions. Over time, this begins to resemble the earliest shadow of evolution. Modern life uses DNA to store genetic information. It uses proteins to perform many tasks, but DNA and proteins depend on each other in complex ways. This creates a puzzle. Which came first? One possible answer is the RNA world. RNA can store information, like DNA. Some RNA molecules can also help chemical reactions happen, like enzymes. If early Earth had an RNA-like stage, then life may have begun with simpler molecules, before cells became more complex. These molecules may have formed in ponds, vents, ice, minerals, or cycles of drying and wetting. The same question matters for other worlds. If self-copying chemistry can arise wherever conditions are right, then life may not be unique to Earth. Somewhere, chemistry may slowly learn the quiet habit of remembering itself. RNA may have been an early bridge toward life. RNA is one of the most important molecules in living things. In modern cells, it helps carry genetic instructions, build proteins, and regulate activity. But RNA may also point backward toward the earliest stages of biology. The RNA world hypothesis suggests that before DNA and proteins dominated life, RNA-like molecules may have done both jobs. They may have stored information and helped reactions happen. This would make RNA a bridge between chemistry and biology. This idea does not answer every question. RNA is not easy to form under simple conditions. It can be fragile. It needs building blocks, energy, and an environment that allows it to survive long enough to matter. Researchers study many possible pathways, including mineral surfaces, warm pools, icy films, volcanic settings, and cycles that concentrate molecules. Still, RNA remains a powerful clue. Modern life carries echoes of it. Ribosomes, the structures that build proteins, rely on RNA at their core. This suggests RNA is not just a helper molecule. It may be a very old part of life's machinery. If life elsewhere uses chemistry similar to Earth's, it may also need a way to store information and copy it. That information molecule might be RNA, DNA, or something different. The universe may have many possible ways to remember. In every living thing, information flows like a quiet stream from the ancient past. Cells need boundaries before they can become worlds. A living cell is not just chemistry floating freely. It has a boundary. A membrane separates inside from outside. This boundary helps the cell keep useful molecules together, manage energy, and protect delicate reactions. Without some kind of compartment, early life may have struggled to become organized. On Earth, cell membranes are made mostly from lipids. These molecules have one end that mixes with water and another end that avoids it. In water, they can naturally form bubbles, sheets, and tiny spheres. Such structures are called vesicles. They can trap molecules inside them, creating simple compartments. This is important for the origin of life. A small compartment allows chemistry to become local. Helpful molecules stay near each other. Energy gradients can form. Reactions can become more efficient. A tiny bubble can become a quiet laboratory. Early membranes may have been simpler than modern ones. They may have formed from fatty acids or other molecules available on young Earth. Some may have grown, divided, or absorbed material from their surroundings. When combined with self-copying chemistry, compartments could have helped early life take shape. On another world, life may also need boundaries. It may use membranes like Earth's, or very different structures adapted to another liquid or temperature. Before life becomes a tree, a reef, or a mind, it may first become a tiny enclosed space. Minerals may have helped early life organize. Rocks are not just passive backgrounds. Minerals can shape chemistry. They provide surfaces where molecules can gather. They can hold charges, guide reactions, and protect fragile compounds. On early Earth, minerals may have helped small molecules join into larger ones. Clay minerals are often studied in origin of life research. Their layered surfaces can attract organic molecules and bring them close together. Other minerals, such as iron-sulfur compounds near hydrothermal vents, may have helped create energy-rich reactions. Mineral pores may have acted like natural compartments, allowing chemistry to concentrate. This matters because early oceans were vast. If useful molecules were spread too thinly, reactions might have been slow. Surfaces and pores create places where chemistry can settle. They give molecules a quiet meeting ground. The link between minerals and life continues today. Bones, shells, teeth, diatoms, and many microbes use minerals. Some bacteria draw energy from reactions involving metals and rocks. Life and stone are deeply connected. On Mars, ancient minerals may preserve traces of past environments. On icy moons, water-rock interactions may create chemical energy. On exoplanets, geology may shape atmospheres and oceans. Life may not begin above rocks, but with rocks inside their cracks and along their surfaces. In the stillness of stone, chemistry may find its first gentle pattern. Wet and dry cycles may concentrate the ingredients of life. Water is essential for life as Earth knows it, but too much constant water can also dilute chemistry. Many origin of life ideas explore places where water comes and goes. A pond may fill with rain, then dry under sunlight. A shoreline may be covered by tides, then exposed to air. A volcanic pool may evaporate, concentrating dissolved molecules. These wet and dry cycles can help molecules join together. When water evaporates, building blocks become more concentrated. Heat and minerals may help them link into longer chains. When water returns, those chains may spread, fold, or become enclosed in tiny droplets. This kind of environment may have existed on early Earth. Shallow ponds, tidal flats, volcanic landscapes, and warm pools all offer changing conditions. Life may not have begun in one perfect place. It may have needed movement between different states: wet, dry, warm, cool, concentrated, and diluted. This idea is important for Mars too. Ancient Mars had lakes, rivers, and perhaps shorelines. If some environments experienced drying and refilling, they may have supported interesting prebiotic chemistry. Even if life never appeared, the chemistry may have moved partway along the path. A planet does not need to be perfectly still for life to begin. Sometimes chemistry needs a rhythm, like water breathing in and out of stone. Ice can preserve and organize chemistry. Ice may seem like a barrier to life, but it can also be useful. When water freezes, impurities and dissolved molecules can become concentrated in tiny liquid channels between ice crystals. These channels can protect molecules from harsh conditions while bringing them closer together. Cold temperatures slow many reactions, but they also preserve delicate compounds. Molecules that break quickly in warm water may survive longer in icy environments. This means ice can become both a shelter and a quiet organizing structure. On early Earth, icy environments may have played a role in prebiotic chemistry. Some researchers study whether RNA-like molecules or other compounds could survive and react within ice. The cold does not stop chemistry completely. It simply slows it into a different rhythm. This is especially meaningful for icy worlds. Europa, Enceladus, Titan, and many distant bodies contain ice. Beneath the surface, there may be liquid water. Within the ice itself, there may be pockets, cracks, salts, and chemical gradients. These are not proofs of life, but they are places where chemistry can be studied. Ice also preserves history. On Earth, ice cores hold ancient air and dust. On Mars or icy moons, frozen layers may preserve old chemical clues. Even in cold silence, molecules may rest close together and wait. Mars may still have protected environments underground. The surface of Mars today is difficult for life as Earth knows it. The air is thin, the temperature is low. Radiation reaches the ground more easily than on Earth. Liquid water is not stable on the surface for long under present conditions. But underground, conditions can be different. Soil and rock can block radiation. Temperatures may be steadier. Salts can change the freezing point of water. Ancient ice may remain buried. If Mars ever had life, the subsurface may have offered a quieter refuge. This is why scientists are interested in drilling, buried ice, caves, and ancient sediments. A dry surface does not always tell the whole story. On Earth, microbes live deep beneath the ground, inside rock pores and fractures. Some rely on chemical energy from interactions between water and minerals. Mars may not be alive today. There is no confirmed evidence of living organisms there. But the possibility of past or hidden habitats keeps the search careful. It asks where water once flowed, where organics may be preserved, and where radiation has not erased old signs. The planet's surface is a red desert, but its deeper layers may remember a softer time. Under dust and stone, Mars may keep its oldest questions sheltered from the sky. Ancient lake beds may preserve signs of past life. If Mars once had lakes, then lake beds are among the best places to look for ancient traces. On Earth, lakes collect fine sediments. These sediments can settle gently, layer by layer. They can trap organic material, minerals, and microscopic structures. Over time, they become a record of the environment. Mars rovers have explored places that appear to have been ancient lake environments. Deltas are especially important. A delta forms where flowing water enters a standing body of water and drops sediment. On Earth, deltas can preserve rich records of past life. A Martian delta does not prove life existed. It only shows that the environment may once have been suitable for preserving clues. If microbes lived in or near the water, some traces might remain in the rocks. If no life existed, the sediments still reveal the planet's climate and chemistry. Searching these rocks is slow. A rover must choose targets carefully. It studies textures, minerals, and chemical signals. It collects samples that may one day be returned to Earth for deeper analysis. Earth laboratories can examine rocks in ways that small rover instruments cannot. This patience matters because the signs may be tiny. Ancient life, if it existed, may not leave obvious shapes. It may leave patterns that only careful instruments can read. In a dried Martian lake, a quiet layer of mud may hold a memory billions of years old. Fossils beyond Earth may not look familiar. On Earth, many fossils are bones, shells, leaves, footprints, or impressions. But the earliest life did not leave large fossils. It left microscopic traces, chemical patterns, layered structures, and changes in minerals. If life ever existed on Mars or another world, its signs may be similarly subtle. This makes the search difficult. A shape in a rock can be misleading. Non-living processes can make patterns that look biological. Minerals can form spheres, filaments, layers, and branching structures. A true fossil must be studied in context. Its chemistry, environment, and formation history all matter. Scientists often look for multiple lines of evidence. A possible fossil shape becomes more interesting if it appears in the right kind of rock, with organic molecules, minerals linked to water, and chemical patterns associated with life. No single feature is enough. This caution protects the search from wishful thinking. It also makes the work more beautiful. The goal is not to find a dramatic object. The goal is to understand a world carefully enough to know what its rocks are saying. Alien fossils, if they are ever found, may not resemble anything in a museum. They may be tiny textures in an ancient stone. They may be chemical shadows. They may require patience rather than awe at first glance. The earliest life does not carve monuments. It leaves whispers in minerals, layers, and time. Sample return could change the search for life. Spacecraft can carry powerful instruments, but Earth laboratories are far more capable. A sample returned from Mars, an asteroid, a comet, or an icy moon could be studied with many techniques. Scientists could examine tiny grains, measure isotopes, search for organics, and look at structures in extreme detail. Sample return is difficult. A spacecraft must collect material, preserve it, launch it from another world or body, and bring it safely to Earth. The process must avoid contamination. Scientists need to know that any possible biological signal is truly from the sample, not from Earth. This is why planetary protection matters. When searching for life, cleanliness is essential. Spacecraft are carefully prepared to avoid carrying Earth microbes to places where they might confuse future discoveries. Return samples are also handled with care, both to protect Earth and to protect the scientific value of the material. A return sample may not contain life. It may contain ancient chemistry, minerals shaped by water, or clues about habitability. Even that would be valuable. Each grain could help reconstruct the history of a distant environment. Some answers are too delicate for distant instruments alone. A small stone brought home can become an entire world under a microscope. Planetary protection keeps the question clean. When spacecraft visit other worlds, they carry pieces of Earth with them. Even after cleaning, tiny traces of biology can be difficult to remove completely. This matters because the search for life depends on knowing what is truly native to another place. Planetary protection is the practice of reducing contamination. It helps prevent Earth microbes from being carried to places like Mars, Europa, or Enceladus. It also helps protect Earth when samples return from other worlds. The purpose is scientific and careful. It keeps the evidence as clean as possible. If Earth microbes were accidentally introduced to a habitable environment, they could confuse future searches. A later mission might detect life and not know whether it came from Earth. Even dead cells or organic residues could create misleading signals. This is especially important for ocean worlds. A moon like Europa may have environments that could, in theory, support life. Any mission that lands or drills there would need extraordinary care. Exploration must be balanced with respect for the unknown. Planetary protection also has a quiet philosophical meaning. It recognizes that other worlds are not just targets, they are natural histories. Their chemistry belongs to them. Their possible life, if it exists, should be studied without being disturbed. To search wisely, humanity must learn to arrive gently. The search for life also teaches how fragile Earth is. Looking outward changes the way Earth appears. Mars shows how a once wet planet can become dry and cold. Venus shows how a rocky world can become intensely heated under a thick atmosphere. Europa and Enceladus show that oceans can hide in darkness. Titan shows that chemistry can be rich without being Earth-like. Each world becomes a mirror. Together they reveal how delicate habitability can be. Earth's oceans, atmosphere, magnetic field, climate cycles, and living systems are not separate things. They interact, they support one another. They have remained balanced across enormous time, but not without change. The search for alien life is therefore also a study of home. By asking where life might exist elsewhere, science learns what makes Earth alive. It learns how atmospheres evolve, how water is lost or preserved, how stars affect planets, and how chemistry becomes biology. This does not make Earth less special, it makes it more visible. From space, Earth is a small blue planet, with clouds curling over oceans. It is the only known place where the universe has become aware of itself. The question, "Are we alone?" reaches outward, but it also returns gently, like starlight, to Earth. SETI listens for intelligence, not just life. The search for extraterrestrial intelligence is different from the search for microbes. A microbe may live quietly under ice or inside rock. It may change chemistry slowly, without ever sending a signal. Intelligence, if it builds technology, may leave marks that can cross space. SETI stands for the search for extraterrestrial intelligence. It is not one single telescope or one single method. It is a long effort to look for signs that another civilization may exist. The most familiar version listens for radio signals. Other versions look for laser flashes, unusual heat, artificial chemicals, or strange patterns that nature may not easily make. The idea is simple and gentle. If another civilization uses technology, some part of that technology might become visible. A signal could be intentional, like a message sent toward other stars, or it could be accidental, like radio leakage from a planet with transmitters. So far, no confirmed alien signal has been found. That does not close the question. The galaxy is wide, and humanity has listened carefully for only a short time. SETI is still young compared with the age of the stars. The search continues because the possible meaning is enormous. One clear signal, confirmed carefully, would show that mind has appeared somewhere else. It would not need to be loud. It would not need to be close. It would only need to be real. Across the quiet sky, listening itself becomes a form of wonder. Radio waves can travel between the stars. Radio waves are a kind of light, but with longer wavelengths than visible light. They can pass through dust more easily than some other forms of radiation. They can travel across great distances. This makes them useful for astronomy, communication, and SETI. Humanity already uses radio waves for many purposes. They carry broadcasts, radar, spacecraft commands, and signals between satellites and Earth. A technological civilization elsewhere might also discover radio. It might use radio to communicate across its own planet, to speak with spacecraft, or to send signals into space. SETI often searches for narrowband radio signals. Natural cosmic sources usually spread their energy across wider ranges of frequency. A very narrow signal, especially one that comes from a fixed point in the sky and repeats, could be interesting. It would still need careful checking. Earth itself is full of radio noise, and many false signals come from human technology. The challenge is not only hearing a signal, it is knowing where to look, what frequency to search, and when to listen. A civilization may transmit for only a short time. Its beam may point in another direction. Its signal may be too weak by the time it reaches Earth. Still, radio remains a peaceful bridge across distance. A simple wave can leave a planet and continue outward for centuries. Laser signals could be another kind of message. Light can also be used for communication. A powerful laser can create a very focused beam. If aimed carefully, it could send information across space. Optical SETI searches look for brief flashes of light that might come from artificial lasers. A laser signal would be different from a broad glow. It might appear as a very short pulse. It might repeat in a pattern. It might come from the direction of a star system. Like radio signals, it would need strong confirmation. Telescopes would need to rule out satellites, aircraft, instrument effects, and natural events. Laser communication has advantages. A beam can carry a lot of information. It can be tightly focused, which saves energy. But that focus also makes it easy to miss. If the beam is not pointed toward Earth, Earth will not see it. This makes optical SETI a patient search. It watches stars and waits for light that behaves in an unusual way. Most nights are ordinary. Most stars shine as stars do. But each observation adds a little more listening to the human story. A civilization might choose radio. It might choose lasers. It might choose something humans have not imagined yet. SETI must remain open, because intelligence may not follow familiar habits. Somewhere, a narrow beam of light may cross the dark without ever touching Earth. Technological life may change a planet's atmosphere. A civilization does not need to send a direct message to be noticed. It may change its planet by using energy, building industry, farming land, or releasing chemicals into the air. Some of those changes could, in principle, be seen from far away. These possible signs are called atmospheric technosignatures. On Earth, technology produces certain gases that are not common in natural atmospheres. Some industrial chemicals would be difficult to explain without technology. If future telescopes studied an exoplanet and found unusual artificial compounds, scientists would examine them very carefully. This idea is delicate. A strange chemical is not automatically a sign of civilization. Atmospheres are complicated. Unknown geology, photochemistry, or measurement errors can create confusion. The star's radiation can change molecules. Clouds and hazes can hide or imitate features. Still, atmospheric technosignatures expand the search. They show that intelligence may be found not only by messages, but by planetary effects. A civilization might be quiet in radio, yet visible in chemistry. It might not be trying to communicate at all. It might simply leave traces of its activity in the air. Earth itself has become a planet changed by life and technology. From far away, its oxygen would speak of biology. Some of its artificial chemicals might speak of industry. A world's atmosphere can become a diary written in invisible ink. Artificial light could glow on a distant night side. Earth's night side is not completely dark. Cities shine along coasts, rivers, roads, and plains. From space, artificial lights reveal human presence. They do not cover the whole planet, but they form patterns unlike lightning, aurorae, or starlight. In theory, a distant civilization might also light its night side. If telescopes were powerful enough, they might detect unusual brightness as a planet turns. The light could appear and fade with rotation. It might be concentrated in certain areas. It might have colors linked to artificial sources. This would be extremely difficult to detect across interstellar distances. A planet is tiny beside its star, and artificial lights would be faint. Current technology is not able to see city lights on Earth-like exoplanets around distant stars. But the idea helps scientists think about future possibilities. Artificial light is a kind of technosignature. It does not require a message. It is simply a sign that a world uses energy in a visible way. A civilization under another sky might light roads, habitats, coastlines, or structures in patterns nature would not easily create. The thought is gentle and strange. Somewhere the night side of a planet could glow with small points of intention. No voice would need to travel. No greeting would need to be sent. A dark world may carry soft lights along its shores. Waste heat may reveal large-scale technology. Every use of energy produces waste heat. Machines, cities, computers, engines, and habitats all release warmth. Even very advanced technology would need to obey this basic rule. Energy does not disappear. It changes form, and eventually spreads as heat. Some scientists search for this idea on very large scales. A civilization using enormous amounts of energy might produce extra-infrared radiation. It might warm a planet, a moon, or large structures in space. This possible sign is called a technosignature of waste heat. The most famous imagined example is a Dyson sphere, or Dyson swarm. This is not usually pictured in science as a solid shell. A more realistic idea is a swarm of collectors orbiting a star, gathering energy. Such structures might block some starlight and re-emit energy as infrared heat. No confirmed Dyson structure has been found. Stars can behave strangely for natural reasons. Dust, disks, stellar activity, and viewing angles can all create unusual signals. Any candidate must be studied with caution. Still, waste heat is an elegant idea because it rests on physics. A civilization can hide messages, but it may be harder to hide energy use completely. If it grows large enough, warmth itself may become visible. In the cold dark between stars, even technology would leave a gentle glow. Interstellar probes may be quieter than radio signals. A civilization might explore space by sending machines instead of messages. Robotic probes could cross between stars, study planets, and report home. This idea is familiar because humanity already sends probes across the solar system. Voyager, Pioneer, New Horizons, and many others show how machines can travel where living bodies cannot easily go. Interstellar probes would face enormous challenges. The distances are vast. Travel could take centuries, millennia, or longer. A probe would need power, durability, guidance, and a way to survive dust and radiation. It might also need to slow down near another star, which is very difficult. Still, probes are possible in principle. A civilization older than humanity might send small fast craft, slow durable craft, or self-repairing machines. They might not broadcast loudly. They might wait, observe, or drift silently through a system. This creates another possibility for the quiet sky. Maybe civilizations do not send powerful radio messages for long. Maybe they explore with instruments. maybe the evidence of intelligence would be local and small, not a signal from far away. Science has no confirmed evidence of alien probes, but thinking about them helps broaden SETI beyond listening alone. Intelligence may leave artifacts, motion, heat, or unusual objects. Between stars, a tiny machine could travel like a seed across a dark field. Interstellar objects visit from other systems. In 2017, astronomers discovered Oumuamua, the first known interstellar object passing through the solar system. It was not bound to the Sun. It came from another star system and continued back into interstellar space. Later, the comet 2I Borisov became another confirmed interstellar visitor. These objects are natural as far as science can tell. They are important because they show that material moves between star systems. Pieces of planets, comets, and asteroids can be scattered into deep space. Some eventually pass through another system. Interstellar objects are not evidence of alien technology, but they remind science that star systems are not completely isolated. They exchange material across long ages. A rock formed near one star can wander past another. An icy body can carry chemistry from its birthplace into a new region of the galaxy. This matters for astrobiology in a gentle way. Organic molecules may travel between systems. Dust and ice may carry chemical histories. The galaxy is not just a collection of separate islands. It is also a slow-moving ocean of debris, visitors, and ancient fragments. Future telescopes may find many more interstellar objects. Some could be studied closely if discovered early enough. They may reveal the chemistry of other planetary systems without needing to travel to them. A small object crossing the solar system can become a messenger from another star's distant shore. The Voyager records are messages to deep time. The Voyager spacecraft carry golden records. These records contain sounds, images, music, greetings, and information about Earth. They were made as symbolic messages from humanity to any future finder, though the chance of discovery is extremely small. Voyager 1 and Voyager 2 are now traveling beyond the planets, far from the Sun. They are not aimed at any specific civilization. They are quiet artifacts moving through interstellar space. Their messages are less like letters with addresses and more like bottles released into a cosmic sea. The records include human voices, natural sounds, and representations of life on Earth. They carry the sound of wind, thunder, birds, and heartbeat. They carry music from different cultures. They carry diagrams meant to show where the spacecraft came from. This matters because it shows how humans imagine contact. Before receiving any message, humanity has already sent a small piece of itself outward. The records are gentle, hopeful, and patient. They do not demand an answer. They simply say that a living world existed here. The Voyagers will likely outlast many human structures on Earth. Long after their instruments go silent, the spacecraft will continue drifting. They may travel for millions of years. A small golden record carries Earth's memory into the long night. Pulsars once seemed almost too regular. In 1967, astronomers discovered pulsars, objects that send out extremely regular pulses of radio waves. At first, their precision was astonishing. The signals arrived with such steady timing that the first source was jokingly nicknamed LGM-1 for Little Green Men. The true explanation became even more beautiful. Pulsars are rotating neutron stars. They are the collapsed cores of massive stars, incredibly dense and spinning rapidly. Beams of radiation sweep through space like lighthouse beams. If Earth lies in the path, radio telescopes detect regular pulses. Pulsars are natural, not artificial, but their discovery is important to SETI because it shows how careful science must be. A strange signal may seem technological at first. Then nature may reveal a deeper mechanism. The universe can make patterns far more precise than expected. This does not make SETI weaker, it makes it wiser. Every candidate signal must be tested against natural explanations. Pulsars, quasars, fast radio bursts, and other cosmic sources all teach caution. They expand the catalogue of what nature can do. At the same time, pulsars became useful. Their timing is so stable that they can help test physics, study gravity, and map space. What first looked mysterious became a new tool for understanding the cosmos. Nature itself can tick like a clock in the dark. Fast radio bursts show the sky still surprises science. Fast radio bursts are brief flashes of radio energy from deep space. They last only milliseconds, yet some release enormous energy. For years, their origins were mysterious. Some repeat, others have been seen only once. Many are linked to distant galaxies. Today, magnetars are a leading explanation for at least some fast radio bursts. A magnetar is a neutron star with an extremely strong magnetic field. Its activity can release sudden bursts of energy. Still, the full population of fast radio bursts remains an active field of research. Fast radio bursts are not evidence of alien technology. They are examples of how the universe continues to produce new puzzles. When a strange signal appears, science must ask every careful question. Is it local interference? Is it a natural source? Does it repeat? Where in the sky does it come from? What else is nearby? For SETI, this is useful training. The sky is rich with natural signals. A true techno-signature would need to stand apart from this richness. It would need patterns that natural processes cannot easily explain. The existence of fast radio bursts makes the cosmos feel alive with activity, but not in a biological sense. Stars, magnetic fields, and compact objects all speak in sudden flashes. Even a millisecond can carry a message from the deep universe, written by nature itself. Contact may not look like a conversation. When people imagine contact, they often imagine a clear message, a greeting, a signal, a reply. But real contact, if it ever happens, may be stranger and slower. It may begin as a chemical pattern in an atmosphere. It may begin as a repeated radio signal with no translation. It may begin as a structure seen only through heat. Science may first know that another intelligence exists without knowing anything personal about it. There may be no faces, no voices, no shared language, and no immediate exchange. The discovery could be a line in a spectrum, a pulse in data, or a pattern of energy. This does not make it less meaningful. Even a silent techno-signature would change humanity's understanding of life. It would show that intelligence is not unique to Earth. It would show that the universe has produced minds more than once. The next step would be patience. Researchers would check the signal. Other observatories would look. Natural explanations would be tested. Years might pass before certainty grows. A discovery of this size would not need speed. It would need steadiness. Contact may be less like meeting a stranger in a room, and more like finding a distant candle across a valley at night. A single confirmed light would be enough to change the darkness. A message from another world might be difficult to understand. If a signal from another civilization were ever confirmed, the next question would be meaning. A signal might prove intelligence without revealing language. It could be a simple pulse, a pattern of numbers, a repeating tone, or a beam carrying information in a format humans do not yet know how to read. Human languages are shaped by Earth. They grow from human bodies, human senses, human histories, and human needs. An alien language would grow from another biology, another environment, and another path through time. It might not use sound. It might not use symbols in a familiar way. It might encode meaning through mathematics, timing, frequency, images, chemistry, or something stranger. This is why many imagined messages begin with simple patterns. Prime numbers, basic geometry, atomic constants, or repeated sequences might be easier to recognize across cultures and planets. Mathematics may not be a language in the human sense, but it can reveal intention. A pattern that nature is unlikely to make could become the first bridge. Understanding would still be slow. Scientists would check the source, confirm the signal, preserve the data, and invite many minds to study it. There might be no quick translation. There might be no clear greeting. The first confirmed message may simply say, in the quietest possible way, that someone made it. Across the stars, meaning may begin as pattern before it becomes speech. Mathematics may be the first shared doorway. Even if alien minds are very different from human minds, they may still live in the same physical universe. Gravity shapes their worlds. Light travels at the same speed. Atoms have the same structures. Circles, ratios, and prime numbers remain themselves, whether they are noticed on Earth or somewhere else. This is why mathematics often appears in ideas about interstellar communication. A sequence of prime numbers could suggest intelligence because it follows an abstract rule. Diagrams based on hydrogen, the simplest atom, might use a shared feature of nature. Pulses arranged into a rectangle might be converted into an image if the receiver recognizes the structure. The Arecibo message, sent in it was a brief symbolic radio message aimed at a distant star cluster. It included numbers, chemical information, a simple human figure, and other encoded details. It was not meant as a practical conversation. It was more like a demonstration of possibility. Mathematics does not solve every problem. A pattern may be recognized, but its meaning may still be unclear. A civilization may think in ways that do not match human assumptions. But mathematics gives a starting point, quieter than language and deeper than culture. Before two worlds can speak, they may simply count together in the dark. Earth has already been leaking signals into space. For more than a century, human technology has produced radio waves. Some remain close to Earth, some travel outward. Broadcast, radar, and communication systems have created a faint expanding shell of human activity, moving through space at the speed of light. This does not mean Earth is easily detectable from anywhere in the galaxy. Most ordinary broadcasts become extremely weak with distance. They spread out. They blend into noise. A distant civilization would need sensitive instruments and a reason to look carefully in Earth's direction. Some signals are stronger, especially radar beams aimed into space. These can travel farther in more focused forms. Still, the detectable period of human technology is tiny compared with cosmic time. From far away, Earth has only recently become a planet with artificial radio noise. This creates a gentle perspective. Human civilization has only just begun to glow technologically. For most of Earth's history, there were no radio signals, no city lights, no satellites, and no spacecraft. Yet the planet was alive. If another civilization is listening, it would need to be nearby enough, capable enough, and listening at the right time. The chance may be small, but the idea is still beautiful. A thin shell of human signal moves outward, carrying traces of a young technological world. Messages sent on purpose are called METI. METI means messaging extraterrestrial intelligence. It is the idea of intentionally sending signals toward other stars. Unlike passive SETI, which listens, METI speaks. It sends a message and accepts that someone somewhere might receive it. This idea creates thoughtful debate. Some scientists and thinkers support it. They see message sending as a natural part of exploration. Earth has already been visible in some ways, and deliberate messages could be carefully designed to represent humanity. Others urge caution. They argue that humans do not yet know enough about possible civilizations to speak for the whole planet. The debate is not only scientific, it is ethical, cultural, and philosophical. Who gets to decide what message Earth sends? What should it say? Which languages, images, music, or symbols should represent a whole living world? Should Earth announce itself, or continue mostly listening? There is no single answer, but the discussion itself shows how serious the question has become. Contact is not only about telescopes, it is also about responsibility. A message to the stars would be a message from Earth, not from one country, one generation, or one group of people. The quietest wisdom may be to listen carefully before speaking loudly, and if Earth ever sends a true greeting, it should be gentle, patient, and shared. Alien life may not look like Earth life. The search for life begins with Earth, because Earth is the only known example, but life elsewhere may not copy Earth's forms. It may use different pigments, different body plans, different senses, different metabolisms, and different ways of moving through its environment. Even on Earth, life is astonishingly varied. A whale, a mushroom, a bacterium, a redwood tree, and an octopus are all living things, yet they experience the world in deeply different ways. Some have eyes, some do not. Some move quickly, some stay rooted, some breathe oxygen, some are harmed by it, some live in boiling water, some sleep through drought. If one planet can produce so much variety, another planet may produce forms that feel unfamiliar from the beginning. Gravity may shape bodies. A thick atmosphere may make floating easier. A dim red star may favor different pigments. A deep ocean may produce life that never sees a surface. A world with no land may never grow forests, but may fill its seas with drifting organisms. This is why scientists try not to search only for familiar creatures. They search for life's functions, energy use, chemistry, reproduction, adaptation, and environmental change. Alien life may not be strange because it is dramatic. It may be strange because it follows its own quiet logic. Carbon is a favorite element for life. Life on Earth is based on carbon. Carbon is useful because it can form many kinds of bonds. It can build chains, rings, sheets, and complex molecules. It joins with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and many other elements. This flexibility makes carbon chemistry rich. Carbon is also common in the universe. It forms inside stars and spreads through space when stars age and die. It appears in interstellar clouds, meteorites, comets, planets, and living cells. The same element that drifts between stars also helps build leaves, muscles, shells, and DNA. It appears in interstellar clouds, meteorites, comets, planets, and living cells. The same element that drifts between stars also helps build leaves, muscles, shells, and DNA. Scientists sometimes imagine life based on other elements, especially silicon. Silicon can form interesting structures and is common in rocks. But silicon chemistry is less flexible in water and at Earth-like temperatures. It tends to form strong bonds with oxygen, creating minerals rather than the shifting molecules life needs. This does not mean non-carbon life is impossible in every environment. The universe may hold surprises, but carbon remains the most promising foundation because it does so many useful things so naturally. The search for alien life, therefore, often looks for carbon chemistry, not because imagination is limited, but because carbon is genuinely powerful. In the deep grammar of matter, carbon writes long and delicate sentences. Water may not be the only possible liquid, but it is a very good one. Life needs a medium where chemistry can happen. On Earth, that medium is water. Water dissolves many substances, moves materials, supports reactions, and remains liquid across a useful range of temperatures. It is polar, meaning its molecules have a slight electric balance that helps them interact with other molecules. Scientists sometimes consider other liquids. Methane and ethane flow on Titan. Ammonia can act as a solvent under some conditions. Some exotic environments might allow chemistry in liquids unfamiliar to everyday life on Earth. But water remains especially useful. It is abundant in the cosmos. It forms from hydrogen and oxygen, two common elements. It exists as ice, liquid, and vapor under conditions found on many worlds. It expands when frozen, allowing ice to float and insulate water below. This one property helps lakes and oceans remain liquid beneath frozen surfaces. The search for water is not narrow. It is practical. It follows the best-known path without insisting it is the only path. A methane lake on Titan may teach chemistry. A water ocean under Europa may invite questions about habitability. Both matter, but in different ways. Life elsewhere might use another liquid, but water is the universe's most familiar gentle solvent. Where water lingers, chemistry finds room to move. Alien senses may be shaped by alien worlds. On Earth, senses are tuned to environments. Eyes respond to light that passes through air and water. Ears respond to vibrations. Noses and tongues respond to chemistry. Skin responds to pressure, heat, and touch. Other organisms sense magnetic fields, electric fields, polarized light, humidity, and tiny chemical traces. Alien life, if it exists, would be shaped by its own world. On a dim planet around a red dwarf, vision might adapt to redder light or infrared limits. In a deep ocean, organisms may rely more on pressure, chemistry, heat, or electric signals. In a thick atmosphere, sound might travel differently. On a high-gravity planet, bodies might stay low and strong. On a low-gravity world, gliding or floating could become easier. Intelligence, too, would be shaped by senses. A species that maps the world through smell, vibration, or electric fields may think differently from a species that relies on vision. Its technology, if it developed any, might follow paths humans would not immediately recognize. This matters for contact. A signal designed for human eyes and ears may not match another mind's natural experience. Communication may need to begin with physics, not sensory familiarity. Every living world would teach its creatures what matters. Under another sky, even awareness may have a different texture. Evolution may repeat useful shapes. Although alien life may be unfamiliar, evolution can sometimes find similar solutions in different places. On Earth, wings evolved in insects, birds, bats, and extinct pterosaurs. Streamlined bodies appear in fish, dolphins, and ichthyosaurs. Camera-like eyes evolved in both vertebrates and cephalopods. This is called convergent evolution. It happens because certain problems have useful solutions. Moving through water rewards smooth shapes. Flying rewards light structures and airfoils. Seeing rewards ways to focus light. Digging, swimming, climbing, and grasping all guide bodies in certain directions. If life exists elsewhere, some forms may echo Earth without being related to Earth. A world with oceans may produce swimmers with streamlined bodies. A world with light may produce organs that detect it. A world with predators and prey may produce camouflage, shells, speed, or senses tuned to motion. But convergence has limits. Evolution works with available materials and histories. Alien life may solve familiar problems in unfamiliar ways. It may use different chemistry, different skeletons, different symmetry, or different movement. The result may be a mixture of the recognizable and the strange. Some patterns may feel almost familiar, others may not. Life may improvise endlessly, yet still return to certain quiet melodies. Intelligence may arise in oceans. Human intelligence developed on land, but Earth's oceans also hold intelligent life. Dolphins communicate and cooperate. Whales sing across great distances. Octopuses solve problems, explore objects, change color, and behave with remarkable flexibility. Cuttlefish, sea lions, and other marine animals also show complex behavior. This raises an interesting question. Could a technological civilization arise in an ocean? Oceans provide rich environments, stable temperatures, and three-dimensional movement. But they also create challenges. Fire is difficult underwater. Metallurgy is difficult. Electricity behaves differently. Building long-lasting tools may be harder without dry land and easy access to combustion. An ocean world might produce intelligence without technology. It might produce memory, culture, communication, and social learning, yet never build radio transmitters. Such a world could be alive and aware, but invisible to SETI. This possibility softens the search for intelligence. Technology is not the only meaningful outcome of evolution. A whale-like mind under another sun would not be less real because it never sends a signal. An ocean full of songs would still be a profound expression of life. Across the galaxy, there may be minds that never touch fire. The universe may contain intelligence that stays beneath waves. Civilizations may choose quietness. A civilization with advanced technology might not broadcast constantly. It may decide that silence is safer, more efficient, or more respectful. It may use tight beams rather than broad signals. It may communicate through cables, lasers, local networks, or technologies that do not leak much energy into space. Humanity itself is changing. Some older broadcasts leaked strongly. Modern communication increasingly uses focused signals, fiber optics, satellites, and digital systems. Over time, Earth may become less radio loud in certain ways, even as it becomes more technologically active. This means a civilization could exist and still be hard to detect. Its technological phase might be brief. Its noisy phase might be shorter still. It might have no interest in announcing itself. It might listen, study, and remain quiet. There is also the possibility of cultural choice. A civilization may value privacy. It may avoid interfering with younger worlds. It may turn inward toward art, computation, biology, or local exploration. Technology does not guarantee expansion or loudness. This idea changes the meaning of silence. Silence may not be absence. It may be preference, efficiency, caution, or simply a different way of living. Among the stars, a quiet civilization would be almost indistinguishable from an empty sky. The zoo hypothesis imagines careful non-interference. One idea about the silent sky is called the zoo hypothesis. It suggests that advanced civilizations might know about Earth but choose not to reveal themselves. They might observe without interfering, the way humans sometimes protect natural habitats from disturbance. There is no evidence that this is true. It is a speculation, not a scientific conclusion, but it remains part of the conversation because it explores one possible reason for silence. If older civilizations exist, they might have rules about contact. They might wait until a younger civilization reaches a certain stage. They might avoid shaping its development. The idea says more about contact than about proof. It asks whether intelligence would always announce itself. It asks whether wisdom might include restraint. It asks whether silence could be intentional. Science cannot rely on this hypothesis because it is difficult to test. A hidden observer leaves no clear evidence. But as a thought experiment, it helps widen imagination. It reminds the search not to assume that every civilization behaves like an expanding radio beacon. The galaxy may be empty of watchers, or it may contain quiet minds with reasons unknown to us. Some possibilities cannot yet be tested, so they remain soft shadows at the edge of thought. The answer may arrive first as uncertainty. If life is ever detected beyond Earth, the first announcement may not be simple. It may not be a clear photograph or an unmistakable signal. It may begin with uncertainty. A gas appears in an atmosphere. A rock contains unusual chemistry. A plume holds complex molecules. A radio signal repeats once, then disappears. Science often advances through careful uncertainty. A strange observation invites more observations. A possible biosignature invites models. A possible signal invites other telescopes. A possible fossil invites microscopes, chemistry, and debate. The public may want a quick yes or no, but the universe rarely answers that way. The search for life may move through stages: interesting, promising, difficult to explain, increasingly strong, and eventually accepted. The first real evidence may be recognized slowly, after many patient tests. This slowness is not disappointing. It is how trust is built. A discovery this deep must be allowed to become sturdy. It must survive doubt, comparison, and time. The first hint of alien life may feel less like a shout and more like dawn. At first, only the edge of the sky grows pale. The first discovery may be simple life, not civilized. The most likely first answer to the question of life beyond Earth may not be a message from the stars. It may not be a city under another sun. It may not be a spacecraft, a voice, or a clear sign of intelligence. It may be something much smaller. It may be a microbe. Microbial life is the most durable and ancient kind of life known on Earth. It appeared early. It survived deep time. It lived through changing oceans, changing skies, impacts, ice ages, and volcanic eras. Long before large animals existed, microbes were already shaping the planet. If life appears easily, then microbes may be the most common living things in the universe. They may live in hidden oceans, damp rocks, salty brines, warm cracks, or buried sediments. They may not make oxygen. They may not build structures. They may not be visible from far away, but they would still be alive. This possibility is gentle and profound. It means the universe may not need to produce intelligence everywhere to be biologically rich. A quiet moon with microbes under ice would still change everything. A fossil cell in Martian rock would still show that life is not only an earthly event. The first discovery may not look dramatic. It may be a chemical pattern, a tiny structure, or a sample that takes years to understand. The smallest life beyond Earth would make the universe feel more awake. The search for life is also a search for life's limits. Every world teaches what life can and cannot do. Earth shows that life can survive heat, cold, acid, salt, pressure, darkness, and radiation when conditions allow. Mars shows how surface habitability can fade. Venus shows how a rocky planet can become intensely altered by atmosphere. Europa and Enceladus show that oceans can hide beneath ice. Astrobiology studies these limits carefully. It asks how much radiation life can tolerate, how little water it can use, how much salt it can survive, what temperatures stop metabolism, how long dormancy can last, what kinds of energy can support living systems. These questions are not only theoretical, they help define where to search. A place may seem harsh to humans but gentle enough for microbes. Another place may contain water, yet lack energy. Another may have chemistry, but not enough stability. Life is flexible, but not infinite. It needs structure. It needs energy. It needs chemistry that can keep moving without falling apart. It needs an environment where information can be preserved and copied. By learning life's limits, science learns where possibility becomes unlikely and where hope remains reasonable. The edge of life is not a sharp line. It is a quiet shore where chemistry and biology meet. Venus reminds science that habitability can be lost. Venus is close to Earth in size and mass. It is sometimes called Earth's sister planet, but its surface is very different. Venus is wrapped in a thick carbon dioxide atmosphere. Its clouds contain sulfuric acid. Its surface is extremely hot, with pressure far greater than Earth's sea level. This makes Venus a powerful lesson. A rocky planet can begin with some similarities and end in a very different state. The details of Venus's past are still studied. It may once have had more water. It may have followed a path where greenhouse warming became extreme, drying and transforming the planet. For the search beyond Earth, Venus is important because it shows that size and location are not enough. A planet near the inner edge of habitability may lose its water. Its atmosphere may become too dense. Its surface may become unable to support life as Earth knows it. Venus also teaches caution in reading distant planets. An exoplanet close to Earth's size may not be Earth-like. It may be more like Venus, hidden under thick clouds and intense heat. Without careful study, a world's true nature can remain concealed. Yet Venus is not only a warning, it is also a neighbor with a deep climate history. Understanding Venus helps scientists understand Earth, Mars, and distant rocky planets. A bright planet in the evening sky carries a quiet lesson about balance. The atmospheres of dead worlds still tell stories. A planet does not need to be alive to be meaningful. Mars, Venus, Mercury, and many exoplanets may hold no life, yet their atmospheres and surfaces reveal how planets change. They show how air escapes, how volcanoes shape climate, how sunlight breaks molecules apart, and how water can be lost. Studying lifeless worlds helps science recognize living ones. To understand a biosignature, scientists must first understand false positives. They must know how oxygen can appear without life. They must know how methane can form through geology. They must know how clouds, hazes, and minerals can imitate biological signs. In this way, dead worlds are teachers. They provide comparison. They show what nature can do without biology. They help build the careful background against which life may one day stand out. A planet without life may still have weather. It may have winds, clouds, volcanoes, minerals, ice, lightning, dust, or oceans of lava in its past. It may be quiet now, but its history can be rich. The search for life depends on understanding the non-living universe too. Only by learning the full range of natural worlds can science recognize the rare signature of a living one. Even silence has texture when a planet is read with care. The Milky Way is only one galaxy among many. The search for life often begins inside the Milky Way, because it is home. Its stars are the closest. Its planets are the easiest to study. Its structure is familiar compared with distant galaxies. But the universe stretches far beyond it. There are hundreds of billions of galaxies in the observable universe. Each galaxy may contain millions, billions, or even trillions of stars. Around those stars, planets may form. Around some planets, moons may orbit. On some worlds, chemistry may gather. This does not mean life is everywhere. Distance makes detailed searching beyond the Milky Way extremely difficult. Individual planets in other galaxies are far beyond direct study with present methods. But the scale changes the feeling of the question. If the Milky Way alone is vast, the universe as a whole is almost beyond imagination. The question, "Are we alone?" may refer not only to one galaxy, but to all of observable space. Even if life were rare, the number of possible worlds may still be enormous. The difficulty is evidence. Science cannot claim life elsewhere simply because the universe is large. It must observe, measure, and confirm. Still, the scale invites humility. A single galaxy is already a sea of stars, and the universe is filled with seas. The observable universe may be only part of the whole. The observable universe is the part from which light has had time to reach Earth since the beginning of cosmic expansion. It is not necessarily the entire universe. Beyond the cosmic horizon, there may be more space, more galaxies, more stars, and more worlds that can never be seen from Earth. This does not directly help the search for life, because science can only study what can be observed, but it deepens the feeling of the question. Humanity asks whether it is alone from one small planet, in one galaxy, inside one observable region of a much larger reality. There may be worlds forever beyond contact. Their light may never reach Earth. If life exists there, it may remain unknowable. This is not a failure. It is part of what it means to live inside a universe with horizons. Science often works with limits. Telescopes have limits. Instruments have limits. Light itself has limits when space expands between galaxies. The unknown is not only something waiting to be solved, some of it may be permanently beyond reach. Yet even this has a calm beauty. The search is not made smaller by limits. It becomes more meaningful because every reachable clue matters. Within the horizon of light, the universe still offers more questions than can be exhausted. Humanity is part of the universe, asking about itself. When humans search for life beyond Earth, the search is not separate from nature. Human beings are made of atoms formed in stars. The calcium in bones, the iron in blood, the oxygen in breath, and the carbon in cells all belong to cosmic history. A telescope is matter arranged to look back at the sky. A question is the universe becoming aware of its own mystery. The search for life is not only about finding others, It is also about understanding what Earth's life means. If life is common, then Earth is one voice in a larger chorus. If life is rare, then Earth is even more precious. If intelligence is rare, then the act of wondering becomes delicate. If civilizations are common but quiet, then patience becomes part of cosmic citizenship. Every possible answer changes perspective, but none removes the wonder. Alone or not alone, Earth remains extraordinary. It is a planet where oceans shine, clouds move, forests breathe, microbes work invisibly, and minds look upward. The question has lasted for generations because it belongs to both science and the heart. It asks what kind of universe this is, and what kind of place Earth holds within it. In asking about distant life, humanity softly discovers the meaning of home. The search may last longer than one generation. The question of life beyond Earth may not be answered quickly. Some parts may be answered soon, others may take centuries. A rover may find ancient chemistry. A telescope may detect a promising atmosphere. A future mission may sample an icy plume. SETI may continue listening across wider bands and longer times. Science often grows this way. One generation builds the instruments. Another improves the methods. Another sees what earlier dreamers hoped to find. The search for life is a long human project, passed from mind to mind like a small flame. This is not discouraging. It is peaceful. Some questions are large enough to outlive individuals. They connect people across time. The first people who wondered about other worlds did not know about exoplanets. The people who first imagined Mars canals did not know the true Martian surface. The people who built early radio telescopes did not know how many planets the galaxy held. Each generation receives a larger universe than the one before. It adds a little more clarity and leaves the rest to those who follow. The answer may come tomorrow, or far beyond the present century. The search remains worthwhile either way. Some questions are not rushed because they are too beautiful to hurry. The answer may be yes in more than one way. There may be life beyond Earth in several forms. Microbes may live under ice. Fossils may rest in ancient Martian rock. Simple organisms may drift in distant oceans. Plant-like life may color an exoplanet's surface. Intelligent beings may exist somewhere, quiet and far away. Civilizations may rise and fade across deep time. Or the answer may be more restrained. Life may be rare. Earth may be unusual. The galaxy may contain many planets, but few living worlds. The search may find chemistry again and again, but not biology. The truth may sit between extremes. Life may be common, but complex life rare. Complex life may happen sometimes, but technology almost never. Technology may arise, but remain quiet. The universe may not be empty, yet still feel silent from Earth. This layered answer may be the most realistic. The question, "Are we alone?" may not have only one yes or no. It may unfold into many answers, depending on whether the search means microbes, animals, minds, signals, or civilizations. The universe often resists simple endings. It gives categories, gradients, histories, and surprises. The answer may not be one door opening. It may be many quiet windows, each looking onto a different kind of life. For now, Earth is the only known living world. This is the most important fact in astrobiology. Life may exist elsewhere. Many places are worth searching. Many planets and moons are deeply interesting. Many discoveries have made the universe feel more promising. But so far, only Earth is confirmed to be alive. That fact does not make the universe empty. It makes Earth luminous. Every bird call, every coral reef, every forest, every field of plankton, every sleeping animal, every human thought belongs to the only known biosphere. The ordinary world becomes extraordinary when seen against cosmic silence. Earth is not large. It is not at the center of the galaxy. It is not the biggest planet, the brightest world, or the oldest place. Yet it holds oceans, air, cells, memory, and awareness. It holds beings who ask whether somewhere else, under another sky, life has also opened its eyes. The search beyond Earth begins here, with gratitude for the one living world already known. Whatever the future discovers, Earth remains the first example. It is the starting point, the comparison, and the home from which all questions rise. Until another living world is confirmed, Earth carries the whole known story of life. A small blue planet shines softly in a very large dark, and so the question remains open. Are we alone? For now, science answers with patience. It has not found confirmed life beyond Earth. It has not received a confirmed message from another civilization. It has not yet seen a living planet around another star. But it has found thousands of planets. It has found oceans hidden beneath ice. It has found organic molecules in space. It has found life on Earth, in places once thought impossible. The question has changed. It is no longer only a dream whispered under the stars. It is now a field of careful study. Telescopes, rovers, orbiters, laboratories, radio dishes, and future missions all carry pieces of the search. The unknown is not empty. It is filled with worlds, atmospheres, moons, chemistry, oceans, rocks, signals, and time. It is filled with places where nature may have tried something beautiful. It is filled with possibilities that science approaches one observation at a time. The answer does not need to arrive tonight. It can remain where it has always been. Somewhere between wonder and evidence, glowing softly at the edge of knowledge. The universe is wide, and the question keeps shining. Now the journey can grow quiet. The search for life has crossed many places tonight. It has moved from Earth's oceans to ancient Mars, from Europa's hidden sea to Enceladus's icy plumes, from Titan's orange haze to planets circling distant stars. It has listened with radio telescopes. It has read atmospheres in starlight. It has imagined microbes, forests, oceans, signals, civilizations, and silences. The universe is not only large, it is patient. It gives its answers in shadows, spectra, ice, dust, chemistry, and time. It lets small planets pass in front of distant stars. It lets moons hide oceans beneath frozen crusts. It lets molecules gather in darkness. It lets questions travel farther than spacecraft. But for now, there is nowhere else to go. Let the stars become soft in the mind. Let Mars settle into its red silence. Let Europa's buried ocean move gently beneath its shell of ice. Let Enceladus breathe pale mist into Saturn's night. Let Titan's amber sky fade slowly into dream. The question can rest for tonight. There is no need to solve the whole universe before sleep. There is no need to know every answer. The unknown can remain peaceful. The stars can keep their distance. The galaxies can keep turning. The hidden oceans can keep moving in the dark. Let the body grow heavy. Let the day loosen its hold. Let each thought drift away like a small light crossing deep space. Breathing can slow now. The mind can settle. The long search can become a quiet shore. You have traveled far enough for one night. From one small living world, the question reached outward. It touched planets, moons, stars, oceans, atmospheres, signals, and silence. It found no final answer, but it found wonder everywhere. And sometimes wonder is enough to carry the mind gently toward rest. If you are still awake and would like to keep drifting, another quiet journey is waiting for you on screen. And if these calm nights bring you a little peace, you are always welcome to return and to wander gently through the cosmos again, one drifting mind at a time. Sleep well, and good night.